Good morning, everyone. It is my pleasure to host this international webinar. My name is Anggita, and on behalf of the entire Civil and Environmental Engineering Technology Seminar, I would like to extend a very warm welcome to all of you. We are pleased to have everyone here and greatly appreciate you for taking time off your busy schedule to join us in this event. Among us in this conference, we are privileged to have experts from Harris Foster Consulting Group, Gary Djojo Bachelor of Engineering Honesty Ph.D. as Senior Structural Engineer, Mr. Dodik Marseno from Patent Holder of Sosrobahu, and Mr. Albert Lim Lum Kong as Senior Geosynthetics Manager from Solmax. Unfortunately, we would like to make an announcement that one of our speakers, Mr. Jimmy Bowie Sudomo from PT Prioritas Teknologi Indonesia, couldn't make the presentation for today due to a health condition. We would also like to extend special thanks to Dr. Yureana Wijayanti as our moderator today, our esteemed laboratory assistants, and to the rest of the attendees for their enthusiasm. We hope you'll learn a lot to find the seminar covering the future of integrated infrastructure and sustainable materials lined up for you today to be fruitful and engaging. To begin this event, I invite everyone to invoke the Almighty and pray with your respective beliefs. And let's take a moment of silence to thank God for gathering all of us today and appreciate the good health He has graced upon each of everyone us to this day. Let us pray. Amen. To formally begin this seminar, I'd like to invite Dr. Oki Setiandito to deliver opening remarks for our attendees.
Thank you, Anggi. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Our distinguished guests, speakers, and respected colleagues and students, it is with great pleasure that I welcome you all to the Civil and Environmental Engineering Technology Seminar, or we call SENS, a monthly event that brings together scholars, professionals, and students to share and discuss the latest trends, innovations, and challenges in the field of civil and environmental engineering. As a head of Bina Nusantara University's Civil Engineering Department, I am honored to be hosting this year's SENS with the theme of Innovation in Construction Technology. This topic is of utmost importance, particularly for Indonesia, a country with so much unrealized potential, especially in terms of construction technology. By emphasizing these themes, I hope that this seminar will inspire everyone present to become innovative problem solvers and to work towards a sustainable future for our communities. Once again, I would like to extend my warmest welcome to all of you, and I wish you a productive and enjoyable SENS. Without further ado, I formally open this 7th Civil and Environmental Engineering Technology Seminar. Enjoy the seminar. Thank you very much.
Thank you, Dr. Oki Setiandito. A few reminders to ensure an uninterrupted event and to achieve a respectable environment. I would appreciate the cooperation for every participant. First, to mute your microphones at all times during the session. Second, any concern or question concerning the topic can be inquired during the Q&A session, either by raise hand function in Zoom or through the chat box after each speaker's presentation. Third, all participants are required to fill an exit ticket before leaving the meeting which will be informed at the end of the webinar. And finally, participants are required to comply with the rules and regulations applied during the seminar. Now, I would like to invite Dr. Yureana to take over and lead the rest of our event. Dr. Yureana, the floor is yours.
Thank you so much, Anggi. Good afternoon, everyone. So today I'm very grateful to be able to become the moderator to this very good event. So today we have 3 speakers, and each speakers will deliver their presentation for 35 minutes. Then Q&A. So all the participants can, during the presentation, can post the question in the chat box, or after the presentation is being delivered, you can also raise hand. Those who write the question in the chat box, I will read it after the presentation is being delivered. So the first presenters, I would like to invite Pak Dodik Marseno Catur Utomo. Firstly, allow me to read his CV. So he is a toll road expert and business development at Sus Capital KFT. His education is he earns a master's degree in system Teknik Jalan Raya from Bandung Institute of Technology and civil engineering degree from Diponegoro University with a very long experience. So just a few here. He is now a toll road expert at Sus Capital KFT Hungary. Previously, he's a commissioner at PT Duta Makmur Property Indonesia and a director at PT Design Management Cipta Utama Consultant Indonesia. So, please share your PPT slides. You have 35 minutes, more or less, for delivering your presentation. And then after that, we will continue for Q&A. Pak Dodik, the floor is yours.
Thank you, Bu Yureana. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, good morning everybody. Salam sejahtera buat kita semua. Izinkan saya menyapa para peserta, terutama dari BINUS University. Yang terhormat Bapak Dr. Insinyur Oki Stiandito, S.T. M.Eng. IPM, sebagai Head of Civil Engineering Department BINUS. Kemudian yang terhormat Pak Andrew John Pierre sebagai Direktur dari Sen Event, kalau nggak salah ya. Kemudian juga yang saya banggakan, kami hormati juga Bapak-Bapak Ibu sekalian, peserta webinar Sen Civil Environmental and Engineering Technology Seminar pagi ini. Pertama-tama kami ucapkan terima kasih atas kesempatan dan undangan yang diberikan oleh BINUS University kepada kami untuk share share pengetahuan kami, share pengalaman kami. Dalam hal ini kami ingin share tentang metode teknologi dengan teknologi Sosrobahu. Mungkin bagi sebagian teman-teman sudah paham, tapi mungkin bagi yang terutama engineer muda mungkin masih belum paham, sehingga mungkin akan sangat bermanfaat. Saya tidak tahu apakah Profesor Made hadir juga dalam webinar ini. Salam yang terhormat buat Prof. Made kalau beliau hadir. Beliau adalah kompatriot kami, Bu, di STJL dulu di Bandung. Selamat pagi, Prof. Sebelum masuk ke materi, mungkin saya ingin menyampaikan harapan bahwa seperti yang tadi saya sampaikan bahwa kita akan mempresentasikan metode konstruksi teknologi Sosrobahu dengan harapan yang pertama adalah memberikan pengetahuan tentang metodologi konstruksi dengan teknologi Sosrobahu. Yang kedua, sebagai engineer, kita harapkan ini akan menjadi tambahan alternatif metode konstruksi yang dapat dimanfaatkan ke depan dalam pembangunan infrastruktur, apapun itu pembangunan infrastruktur. Kemudian yang ketiga juga sejalan dengan yang disampaikan oleh Pak Oki tadi, akan membangkitkan, menambah motivasi pada kita ya, menginspirasi kita untuk membuat berbagai inovasi teknologi konstruksi yang bisa digunakan di Indonesia maupun di mancanegara. Karena teknologi Sosrobahu ini juga selain digunakan di Indonesia juga di beberapa negara. Mohon izin Bu, saya bisa share materi yang kita sampaikan.
Silakan Pak.
Apakah sudah bisa terlihat?
Sudah Pak.
Sudah, oke. Oke. Dalam presentasi ini kita akan
bisa di full
ya,
screen, Dodi.
sebentar. Sudah?
Ya, sudah Pak.
Oke. Jadi secara umum presentasi yang akan kita lakukan terbagi menjadi dua bagian. Yang pertama kita akan mencoba mengutarakan apa sih teknologi Sosrobahu, konsepnya, sejarah dan penggunaan teknologi ini, kemudian juga penggunaan yang sudah dilakukan untuk proyek infrastruktur jalan layang baik di Indonesia maupun di luar negeri. Kemudian pada bagian kedua kita akan coba membahas lebih detail terkait dengan teknologi ini, bagaimana kita implementasi teknologi ini, evaluasi yang dilakukan, kemudian bagian termasuk dimensi daripada Sosrobahu ini, material yang digunakan, pelaksanaan, keuntungan dan kerugian dari teknologi ini. Jadi kita akan buat dua bagian. Kita masuk yang pertama, Bu. Mohon maaf ini agak cepat karena takut nanti waktunya tidak cukup, Ibu ya. Secara umum bahwa ini yang kebanyakan kita salah, Bu, bahwa Sosrobahu ini adalah teknologi yang merupakan alat bantu konstruksi. Jadi teknologi Sosrobahu ini bukan bagian dari struktur. Jadi ini hanya alat bantu konstruksi yang berupa alat putar bebas hambatan yang dipatenkan. Jadi teknologi Sosrobahu adalah teknologi alat putar untuk membantu dalam pelaksanaan konstruksi. Jadi intinya dia bisa memutar struktur yang berat. Jadi dalam pembuatan jalan layang, pembuatan dan pengucuran pierhead dapat dilakukan paralel. Jadi kemudian diputar. Jadi itu untuk konstruksi jalan layang itu untuk memutar pierhead. Tapi tidak tertutup kemungkinan bahwa ini juga bisa digunakan untuk konstruksi yang lain karena fungsinya adalah sebagai alat putar. Jadi kalau kita lihat di gambar ini di bagian bawah, bagaimana kita melakukan pengecoran pierhead bisa dilakukan secara paralel terhadap existing jalan, kemudian kita putar di posisi yang kita harapkan, biasanya sekitar 90 derajat. Kemudian kalau kita lihat ini juga sebetulnya ini sudah cukup mendunia, sudah pernah diulas juga teknologi ini dalam National Geographic Channel pada tahun 2011. Dan nanti inventornya kita bahas lebih jauh adalah Bapak Insinyur Cokorda Raka Sukawati atau Pak Rake, yang kita kenal sebagai Pak Rake. Next. Kemudian kenapa, bagaimana teknologi Sosrobahu ini bisa idenya bisa timbul begitu ya. Jadi ini dimulai pada saat Indonesia membangun jalan layang tol pertama pada tahun 1987. Jalan tol itu adalah jalan tol Cawang Tanjung Priok. Itu adalah jalan tol layang pertama di Indonesia. Pada saat itu jalan tol ini berfungsi untuk menghubungkan antara jalan tol existing, jalan tol Jagorawi dengan pelabuhan Tanjung Priok. Pada saat itu, tahun 1987, lahan sepanjang cawang Tanjung Priok sudah cukup padat. Sedangkan untuk melakukan pembebasan lahan sudah sangat mahal dan sulit. Kemudian juga pier-head yang digunakan karena jalan tol ini rencananya adalah 6 lane, 2x3. Jadi panjangnya lebih dari 25 meter atau lebih lebar dari jalan existing pada saat itu. Sehingga timbul permasalahan bagaimana kita harus mengecor pier-head tanpa pembebasan lahan pada saat itu. Kemudian yang ketiga adalah jalan existing ini, Cawang Tanjung Priok adalah jalan yang sangat penting pada saat itu dengan nilai ekonomi tinggi karena sebagai jalan penghubung ya antara pelabuhan Tanjung Priok dengan sebelah selatan dan sebelah timur dan barat daripada Jakarta ya, sehingga nilai daripada ekonomi dari jalan tol ini sangat tinggi sehingga kemungkinan untuk ditutup untuk pembangunan adalah sangat kecil. Dari problem tersebut, kemudian ada beberapa solusi yang ditemukan. Yang pertama adalah jalan tol akan dibuat di atas jalan existing Cawang Tanjung Priok. Tapi kemudian timbul permasalahan lain adalah bagaimana kita harus mengecor pierhead. Karena seperti yang tadi disampaikan, lebarnya cukup besar, lebih dari 25 meter. Kalau kita menggunakan metode konvensional dengan shoring, scaffolding, harus menutup jalan, tidak mungkin. Kemudian kalau kita harus menggunakan, ada ide dengan menggantung kepala tiang juga pada saat itu, ide ini muncul dari Pak Rake, tapi kemudian dengan alasan safety, kemudian juga masih harus tetap menutup sebagian jalan, sehingga hal ini tidak dilakukan juga. Kemudian sebenarnya ada metode lain, yaitu adalah metode segmental, di mana kita mengecor ya gas, kemudian kita pasang satu-satu. Tapi juga problemnya adalah pada saat pemasangan pierhead, karena ini butuh waktu yang lama, kemudian juga mengganggu trafik juga. Dari sini kemudian Pak Rake pada saat itu Pak Cokpolda ini sebagai Direktur Utama Karya, jadi beliau pada saat itu sebagai Kepala Pelaksana Proyek untuk Jalan Tol Cawang Tanjung Priok. Dan beliau ini hobi koleksi mobil, Bapak-bapak. Jadi saya pernah ke rumah beliau juga, jadi beliau memang punya banyak koleksi mobil dan tidak heran. Jadi pada saat beliau mendongkrak mobil, dongkraknya ditaruh tengah, kemudian mobilnya bisa berputar gitu ya. Jadi idenya semacam itu. Dari itu beliau berpikir, ini bisa kita lakukan juga untuk pierhead gitu. Jadi dengan konsep hidrolik, jadi seperti dongkrak ya, pompa hidrolik, kemudian kita putar gitu. Pada saat itu alat ini dinamakan sebagai landasan putar bebas hambatan 80, LPBH 80. Kenapa 80? Karena diameter daripada alat ini adalah 80 cm. Kemudian pada saat pemutaran pertama, pada tanggal 27 Juli 1988, Presiden Soeharto memberi nama alat ini sebagai Sosrobahu. Arti dari Sosrobahu dalam bahasa Jawa adalah 1000 bahu. Jadi arti Sosrobahu adalah semacam 1000 bahu yang bisa memutar begitu kurang lebih ya. Kemudian sebetulnya apa penggunaan yang paling efisien untuk teknologi ini? Jadi dengan konsep pengerjaan struktur yang dapat dilakukan paralel kemudian diputar, teknologi Sosrobahu cocok digunakan untuk konstruksi dengan tempat kerja yang relatif sempit karena keterbatasan lahan, mahal dan sulitnya pembebasan lahan. Jadi kondisi ini biasanya ada dari perkotaan. Jadi pengalaman kami memang teknologi Sosrobahu ini kebanyakan digunakan di daerah urban, perkotaan. Ada tiga kondisi yang selama ini kita laksanakan dengan menggunakan Sosrobahu. Yang pertama adalah kondisi konstruksi jalan layang atau struktur di atas existing jalan yang kita lihat di bawah sebelah kiri. Ini baik di atas existing jalan tol ataupun jalan biasa. Ini yang sudah pernah kita lakukan. Kemudian yang kedua adalah kondisi konstruksi jalan layang di samping sungai dan jalan. Jadi ini ada kondisi khusus juga karena ketersediaan lahan di samping sungai dan jalan. Ini semacam jalan tol Becayu. Kita lihat dalam gambar sebelah kanan atas. Kemudian yang ketiga adalah kondisi konstruksi jalan layang atau struktur di atas atau di samping rel kereta api. Ini kita juga ada beberapa kasus. Yang pertama di Jogja, flyover, tapi hanya sedikit yang menggunakan Sosrobahu karena memang flyover. Kemudian yang kedua di Filipina, ini luar biasa karena lahannya sangat sempit. Sebelah kiri kanan adalah rel kereta dan jalan dan rumah penduduk. Jadi ini ada 3 kondisi yang selama ini cukup efektif menggunakan teknologi Sosrobahu. Kemudian kita lihat proyek infrastruktur apa aja dalam hal ini. Selama ini yang digunakan dengan Sosrobahu adalah jalan layang. Kita lihat Sosrobahu ini sudah mendunia, jadi tidak hanya digunakan di Indonesia, tapi juga negara-negara lain ya seperti Malaysia dan Filipina. Jadi kita cukup bangga sebetulnya bahwa mahakarya anak bangsa Indonesia bisa digunakan di luar Indonesia ya, cukup banyak juga. Di Indonesia kita lihat digunakan di jalan tol Cawang Tanjung Priok, kemudian jalan tol Tanjung Priok Pluit, flyover Janti Jogja, kemudian flyover Pamanukan Jawa Barat. Setelah itu memang kita tidak ada proyek infrastruktur yang cukup besar ya, terutama untuk jalan layang. Baru kemudian pada tahun 2017 ada proyek jalan tol layang cukup besar di Indonesia, yaitu jalan tol Jakarta Cikampek 2 Elevated atau sekarang yang kita sebut sebagai jalan tol MBZ ya. Jadi sebagian besar jalan tol ini menggunakan teknologi Sosrobahu. Sebagian menggunakan segmental untuk bagian yang tidak terlalu padat trafiknya setelah KM30 kalau nggak salah. Kemudian jalan tol Cimanggis-Cibitung tahun 2019 ya, ada sebagian segmen yang menggunakan Sosrobahu. Kemudian yang terakhir adalah jalan tol Becayu, Bekasi, Cakung, Kampung Melayu. Ini yang baru saja diselesaikan, dibuka kalau nggak salah tahun ini ya, untuk ruas sampai Bekasi. Untuk di Filipina cukup banyak juga, jadi kebetulan saya sempat bertugas di sana di Filipina, jadi kita sangat terbantu dengan Sosrobahu. Kita waktu itu sempat membangun beberapa jalan layang tol dengan teknologi Sosrobahu, dan cukup yang membanggakan adalah kita juga membangun jalan tol layang pertama di Filipina. Jadi kalau mungkin bapak-bapak familiar dengan kondisi di Manila, Filipina, jalan layang yang ada di sana itu sebagian besar kita bangun dulu. Ada jalan tol Metro Manila Skyway tahap 1, kemudian stage 2, stage 3, termasuk jalan tol Ninoy Aquino Airport. Jadi itu yang menghubungkan ke airport. Terakhir adalah jalan tol North Luzon, Enlek, dan South Luzon Expressway Connector Road. Itu yang baru saja selesai tahun 2023. Untuk Malaysia, kita gunakan di jalan tol Kuala Lumpur Middle Ring Road 2, cukup lama, tahun 1998. Kita coba melihat satu-satu jalan tol yang digunakan dengan teknologi Sosrobahu. jalan tol Cawang Tanjung Priok. Ini adalah jalan tol yang dibangun di atas jalan existing. Jadi jalan existingnya bukan jalan tol, ini ada jalan biasa. Hanya ini jalan-jalan yang seperti yang tadi saya sampaikan mempunyai nilai akses ekonomi yang cukup tinggi sehingga harus menggunakan teknologi Sosrobahu. Ini pertama ya yang menggunakan Sosrobahu. Kemudian yang cukup besar lain adalah jalan tol Japek Elevated. Ini juga luar biasa karena dibangun di atas existing jalan tol, dan yang menarik adalah pada saat pembangunan jalan tol Japek 2 Elevated, di sebelah kiri kanannya juga sedang dilakukan pembangunan. Yang pertama adalah konstruksi LRT, kemudian yang kedua kereta cepat, sehingga betul-betul pemanfaatan lahan yang sempit ini sangat penting, sehingga terasa sekali pada saat itu bagaimana teknologi Sosrobahu ini bisa mengefisienkan ya konstruksi pembangunan pada saat itu. Kemudian jalan tol Cimanggis-Cibitung ini adalah jalan tol yang sebagian ruasnya sekitar 800 meter atau 18 pir. Mungkin kalau kita familiar dengan jalan tol Jalan Cibubur, Jalan Raya Cibubur, sebagian jalan tol ini itu berada di atas Jalan Raya Cibubur, dan dengan kondisi lalu lintas yang cukup padat di daerah Cibubur, kemudian kita diputuskan menggunakan teknologi Sosrobahu sehingga ada sekitar 800 meter atau 18 pir menggunakan teknologi Sosrobahu. Dan yang luar biasa dari jalan tol ini adalah jalan tol ini cukup lebar. Jadi kalau tidak salah segmen yang berada di atas Jalan Raya Cibubur ini adalah segmen dengan super elevasi. Jadi ada sedikit kemiringan, kemudian sedikit berbelok gitu ya. Jadi lebar daripada pierhead-nya cukup besar, di atas 30 meter, kalau nggak salah 34 meter. Kemudian dengan kondisi itu kita memutuskan untuk melakukan modifikasi dari Sosrobahu awal yang tadinya digunakan atau diciptakan oleh Pak Rake dengan diameter 800, kemudian kita rubah menjadi diameter 1300. Jadi ini adalah jalan tol pertama Cimanggis-Cibitung dengan lebar lebih dari 30 meter yang menggunakan Sosrobahu dengan diameter 1300. Kita lihat juga di bawah ini sempat pada saat pemutaran Pier 13 pada tanggal 11 September 2019 dihadiri juga oleh peserta Conference of Asian Federation of Engineering Organization (CAFIO). Jadi memang teknologi ini cukup menarik, tidak cuma engineer kita ya, tapi juga engineer dari beberapa negara termasuk negara-negara ASEAN. Yang terakhir ini yang cukup menarik adalah jalan tol layang Bekasi ke Cakung Kampung Melayu. Berbeda dengan tadi dua jalan tol ini menggunakan Sosrobahu karena kondisi lainnya sempit di antara sungai dan jalan. Jadi antara sungai dan jalan kalau kita lihat di gambar sebelah kiri itu hanya sekitar 8-10 meter. Sementara lebar dari pier yang bersama ini 6 lane, jadi sekitar 27 meter lebarnya, sehingga masih ada sisa hampir 15 meter lebih ya yang di luar daripada lahan ini, sehingga diputuskan untuk menggunakan Sosrobahu, which is ini sangat efektif. Jadi ini segmen dari depan Masjid Al-Azhar sampai Mall Metropolitan ini bisa selesai dengan cepat, meskipun kemudian problemnya terhambat untuk operasional karena di rem yang di ujung di Bekasi yang kemudian terlambat. Next kita coba melihat di penggunaan di Filipina. Jadi seperti yang tadi saya sampaikan, kalau kita lihat peta Metro Manila, jadi peta Metro Manila hampir sama dengan Jakarta. Ini kita balik di oceannya itu sebelah kiri ya, sebelah barat. Jadi bagian yang kita coba highlight ini adalah di urban. Jadi ini adalah bagian yang menggunakan jaringan jalan tol yang menggunakan Sosrobahu. Jadi hampir semua jaringan jalan tol di Metro Manila di urban ya, yang elevated itu menggunakan Sosrobahu. Ini ada Metro Manila SKW S1, S2, Naya, kemudian juga NLEX connector. Kita coba lihat satu-satu. Ini jalan tol Manila S1 dan 2. Ini sebetulnya lebih awal daripada Japek elevated. Jadi kalau Japek elevated di atas, dibangun di atas jalan tol dengan Sosrobahu. Di Manila pada saat tahun 1997 itu kita sudah menggunakan teknologi ini untuk membangun jalan tol di atas existing jalan tol. Jadi hampir sama, ini malah lebih areanya lebih sempit lagi karena jalan tol existingnya 2x3, jadi 6 lane. Sementara medianya hanya sekitar 2 meter. Jadi lahannya benar-benar sangat sempit. Dan kalau kita lihat bisa dibangun dengan sangat rapi, secara paralel, kemudian kita putar satu persatu. Ini adalah Metro Manila SKW S3 dan Naya. Mungkin saya akan lebih ekspos ke Manila, ke airport expressway yang di Manila. Mungkin kalau bapak-bapak familiar dengan Filipina, saya selalu menyebut bahwa bandara airport di Manila itu adalah airport paling bagus sedunia, bukan karena bagus bandaranya, tapi bagus lokasinya. Bayangkan bandara ini berlokasi di tengah kota, jadi kita bayangkan kita ada di misalnya CBD-nya Sudirman, CBD daerah situ ya. Bandara ini mungkin berlokasi sekitar Grogol, jadi hanya sekitar kurang dari 5 km dari CBD. Jadi bisa dibayangkan bagaimana crowded-nya bandara ini, terutama pada saat hari-hari besar ya, misalnya ada Christmas, kemudian hari-hari besar lain, sehingga memang perlu dibuat jalan tol, jalan akses begitu ya ke airport, sehingga penggunaan Sosrobahu sangat bermanfaat pada saat itu. Ini yang baru saja kita kerjakan juga. Ini adalah pembangunan jalan tol yang berada di pinggir rel kereta api. Jadi lokasinya benar-benar di pinggir kereta api. Kalau kita lihat di bawah, ini lokasi kerjanya itu lebih sempit ya. Mungkin kita lihat ini ada rel kereta api sebelah bawah, kemudian sebelah atasnya ini sudah ada jalan akses di perumahan. Jadi lahan kerjanya sangat sempit, hanya sekitar 6-8 meter. Dan ini yang luar biasa karena kadang-kadang pada saat pemutaran itu ujung daripada pierhead itu benar-benar sudah dekat sekali dengan rumahnya. Dan yang cukup hebatnya lagi, ini jalan tol ini dibangun pada saat COVID. Jadi pada saat COVID, semua negara ditutup, termasuk Filipina. Jadi tim Sosrobahu tidak bisa hadir di Filipina, sehingga kita putuskan untuk melakukan supervisi online. Jadi pemasangan daripada Sosrobahu, ya, instalasi, kemudian pemutaran, itu kita lakukan online. Dan alhamdulillah sekitar lebih dari 60 unit bisa kita putar dengan aman saat itu. Itu baru selesai tahun yang lalu, pemutaran terakhir, dan saat ini sudah dioperasionalkan. Oke, kita akan coba masuk ke bagian kedua. Kita coba lebih discuss lebih detail terkait dengan teknologi Sosrobahu. Kita lihat semenjak Sosrobahu ini diperkenalkan, dibuat oleh Pak Rake tahun 1988, sudah ada 3 tipe Sosrobahu yang saat ini kita ada ya, kita gunakan. Yang pertama adalah yang diciptakan oleh Pak Rake tahun 1988. Kemudian yang kedua pada saat digunakan pertama di Filipina itu tahun 1996. Ini masih menggunakan diameter 800. Yang membedakan dengan original Sosrobahu adalah ada penambahan sayap untuk angkor bolt untuk memudahkan pemasangan. Dan ini digunakan pertama di Filipina, Metromanagement Skyway Project Filipina. Jadi memang kita tim Sosrobahu mencoba selalu melakukan improvement terhadap Sosrobahu untuk melihat bagaimana ini bisa dilakukan lebih baik lagi, lebih efisien dan efektif pada saat pelaksanaan. Kemudian tipe yang ketiga, ini yang kita buat pada tahun 2018. Ini adalah Sosrobahu dengan diameter 1300. Jadi ini luar biasa besar. Jadi berat daripada spearhead yang bisa diputar ini lebih dari 1000 ton. Dan ini yang kita gunakan pertama di jalan tol Cimanggis Cibitung. Kita coba lihat lebih detail bagian daripada Sosrobahu ini. Sebetulnya ini sayang ya, mungkin kalau kita bisa melakukan ini offline, mungkin kita bisa melihat micro atau prototype dari Sosrobahu, kita akan lebih jelas begitu ya. Tapi secara umum kita lihat bahwa Sosrobahu ini ada 2 bagian, Bapak-bapak, Ibu-ibu. Yang pertama adalah piringan atas, seperti kita lihat sebelah kanan ya. Kemudian adalah piringan bawah. Jadi seperti kalau orang bilang seperti martabak begitu ya, cetakan martabak. Jadi sangat simpel sebetulnya. Kita lihat ada 2 bagian seperti ini. Dan apa sih komponen yang penting daripada Sosrobahu ini? Yang pertama adalah tentu saja angkor bolt, karena angkor bolt ini akan adalah bagian yang akan mengikat bagian bawah dari Sosrobahu dan bagian atas dari Sosrobahu ke dalam kolom dan spearhead. Kemudian adalah yang kedua adalah Sosrobahu ini ada pipa oli, jadi kita sebut inlet dan outlet. Ini akan bagian di mana kita akan menggunakan oli pada saat pemutaran. Ini kita lihat di ini ada inlet dan outlet. Dan yang terakhir yang sangat penting, ini kalau kita lihat di sebelah kiri bawah, ini ada rubber seal, Pak. Ini yang bagian bawah sebelah kiri, ini ada 2 hitam bundaran di ini antara piringan bawah dan atas ini ada 2 rubber seal. Ini adalah seal yang akan mencegah oli pada saat kita kasih tekanan untuk pemutaran untuk dapat keluar dari Sosrobahu ini. Jadi ini adalah bagian yang sangat penting, rubber seal daripada Sosrobahu ini. Ini diameter ukuran dimensi daripada Sosrobahu ada 2, yang 800 dan 1300. Untuk yang 800 ini diameter luarnya 810 mili, kemudian untuk yang 1300 1360 mili, ketebalan untuk yang 800 adalah 110 mm, kemudian ketebalan yang 1300 145 mm. Kemudian kapasitas ini berapa sih berat spearhead yang bisa diputar dengan Sosrobahu 800 dan 1300. Untuk yang 800 itu sekitar 500 ton. Jadi struktur atau dalam ini kalau jalan layang spearhead yang bisa diputar dengan Sosrobahu di meter 800 ada sekitar 500 ton. Plus 10% lah ya, ini masih bisa kita tolerir, jadi sekitar 500 50 ton, sedangkan yang diameter 1.300 itu bisa memutar pierhead sekitar 1.300 ton, cukup besar. Kemudian hydraulic pressure, ini adalah hydraulic yang pressure yang kita berikan pada saat kita memutar, itu kita ada semacam angka psikologis maksimal di sekitar 78 kg per cm persegi ya. Kita materialnya ada FCD 50, kita lihat. Jadi material yang digunakan di Sosrobahu ini adalah FCD, Ferrocasting Ductile 50. Jadi kalau kita lihat FCD ini kan lebih material yang lebih ulet ya, lebih ulet, lebih kuat dibanding dengan tulangan biasa. Dia juga mempunyai sifat lebih tahan terhadap karat dibanding besi besi baja biasa. Dan yang digunakan untuk Sosrobahu ini ada FCD 50. Ini adalah hasil penelitian dari Pak Rake pada saat itu yang digunakan untuk membuat Sosrobahu. Kemudian bagaimana pelaksanaan daripada Sosrobahu dalam hal ini untuk konstruksi jalan layang. Jadi kita sebenarnya sangat umum, sangat biasa, dimulai dengan fondasi dari foundation, bagian foundation itu bisa dilakukan dengan bore pile atau pile cap untuk konstruksinya, bisa bore pile atau mungkin tiang pancang begitu. Kemudian pile cap yang ini kita lihat di gambar nomor 1. Kemudian kita lanjutkan dengan konstruksi daripada kolom. Dan ini yang menguntungkan kalau kita menggunakan Sosrobahu, karena pada saat kita sudah selesai melakukan konstruksi kolom, kita bisa menggeser pagar ini ke lebih kecil lagi ya. Jadi kita hanya perlu sedikit space untuk membuat pierhead, karena pierhead bisa kita lakukan paralel terhadap jalan. Kita lihat di gambar nomor 4 ini setelah konstruksi kolom selesai ya, ininya bisa kita geser lagi. Kemudian di gambar nomor 5 kita lihat bahwa konstruksi pierhead bisa kita lakukan paralel terhadap jalan existing ya. Sebelum akhirnya di gambar nomor 6 ini kita lakukan pemutaran pierhead. Kemudian kita lanjutkan dengan superstructure construction, dan ini bisa dilakukan sebetulnya dengan kondisi lalu lintas di bawah masih bisa jalan karena kita bisa menggunakan safety net dan sebagainya. Kemudian bagaimana kita memasang Sosrobahu, karena Sosrobahu ini kan instalasinya antara kolom dan pierhead. Jadi kita mulai dengan instalasi template. Kalau kita lihat di gambar sebelah kiri atas, jadi kita siapkan template ini sebelum kita cor kolom. Template ini kita pasang. Jadi yang rumus yang paling penting dalam Sosrobahu ini adalah elevasi. Jadi elevasi ini harus sehorizontal mungkin. Jadi peran dari teman-teman ukur ini sangat penting untuk memastikan bahwa elevasinya itu adalah benar-benar horizontal. Ya. Jadi setelah kita instalasi template, kemudian kita cor kolom, itu akan muncul seperti yang di gambar pertama ini. Jadi ada semacam kayak cetakan untuk Sosrobahu. Nah ini yang kemudian kita lakukan instalasi Sosrobahu yang kedua. Jadi kita lihat yang kedua setelah ada cetakan yang sudah terbuat, ya, kemudian kita install Sosrobahu. Jadi secara umum kalau kita lihat potongan lintangnya itu seperti di gambar sebelah kanan. Jadi kita bisa melakukan elevasi yang sebenar-benarnya daripada Sosrobahu ini. Kemudian di bawahnya juga masih ada space. Ini yang nanti akan kita growting ya. Setelah posisi Sosrobahu yang kita harapkan sudah benar tercapai. Dan ini kita lihat setelah posisi Sosrobahu sudah benar-benar yang kita harapkan, kemudian kita growting. Kita fixing, growting, jadi bagian bawah dari ini, dari Sosrobahu ini akan kita growting. Dan ini juga akan sangat penting karena bagian bawah dari Sosrobahu ini akan menjadi bagian tumpuan pada saat pemutaran. Jadi kualitas daripada growting ini juga harus benar-benar kita perhatikan dalam hal ini. Kemudian langkah selanjutnya setelah ini kita growting, setelah kita install, kemudian kita growting, ini kita membuat semacam gap dilatasi. Jadi ini yang membedakan Sosrobahu dengan konvensional. Jadi untuk teknologi Sosrobahu kita harus membuat semacam gap antara pierhead dan kolom. Tujuannya agar pierhead nanti bisa diputar gitu ya dengan adanya gap ini. Jadi gap ini kita install ada 3 bagian, nanti kita jelaskan apa aja bagian daripada gap dilatasi ini. Setelah gap dilatasi ini selesai, kemudian kita langsung memasukin pekerjaan pierhead seperti normal, pembersihan, kemudian coat pierhead dan sebagainya. Nah, ini setelah lebih detail bisa kita lihat ini adalah kurang lebih potongan melintang daripada Sosrobahu yang terpasang di kolom dan pierhead. Jadi kita lihat ada angkor, kemudian ada 3 layer untuk gap dilatasi yang tadi saya sampaikan. Jadi first layer itu merupakan wooden panel. Jadi ini seperti multiple biasa, tebalnya biasanya sekitar 6 mm. Kemudian bagian kedua, second layer-nya adalah fine sand. Jadi sebetulnya simpel aja, hanya pasir halus kering, pasir halus kering. Ya, ini secara total biasanya gap dilatasi ini sekitar 25 sampai 30 mm, sehingga untuk second layer-nya biasanya kita buat sekitar 15 mm lah, karena bagian terakhir atau third layer daripada gap dilatasi adalah steel plate. Jadi ini steel plate adalah bagian terakhir. Jadi pada saat setelah selesai pierhead ini dicor, kemudian steel plate ini adalah bagian kita lepas pertama. Jadi steel plate kita lepas, kita tarik, kemudian sebelum tadi lupa, ini jadi dipasirin untuk mencegah dia keluar daripada gap ini. Itu ada semacam stopper dengan wooden juga. Jadi yang hijau ini adalah stopper yang kita pasang untuk menghindari pasir keluar daripada gap ini. Jadi tadi setelah selesai pierhead dicor, kemudian steel plate-nya kita lepas, kemudian fine sand-nya kita tiup, ya kita bersihkan. Yang terakhir wooden panel-nya juga kita cabut. Itu akan tercipta sebuah gap antara pierhead dan kolom. Ya. Dan ini ada satu bagian lagi yang penting tadi yang saya sampaikan adalah inlet dan outlet. Jadi ini kurang lebih ilustrasi seperti ini. Jadi inlet dan outlet ini akan muncul nanti sampai permukaan pierhead, sampai permukaan atas dari pierhead. Dan ini akan nanti kita gunakan untuk memberikan oli ya, tekanan melalui inlet dan outlet ini. Ini pemutaran daripada Sosrobahu. Jadi sebetulnya Sosrobahu ini pemutarannya sangat singkat, biasanya sekitar 30 menit sudah selesai dilakukan. Dan selama ini kita masih menggunakan bantuan crane untuk memutar. Hanya memang sangat ringan ya, jadi untuk crane ukuran 25 ton masih cukup. Karena sebetulnya secara teori kanan yang kita berikan melalui oli ya, itu untuk memutar itu akan sangat tergantung terhadap berapa besaran tarikan yang kita perlukan. Jadi sebetulnya kalau tekanan yang kita berikan terhadap oli ini sama besarnya ya, yang menimbulkan tekanan sama besar dengan pierhead, itu secara teori kita hanya dengan tangan aja bisa terputar ini. Sosrobahu, karena kan ada aksi reaksi ya. Jadi dari pierhead ini ada reaksi, kita berikan oli untuk memberikan tekanan reaksi ya terhadap pierhead ini, sehingga akan kalau zero itu artinya tidak ada gesekan sama sekali, jadi bisa kita putar secara mudah. Tapi itu secara teori. Jadi pada kenyataannya pada saat kita sebelum pemutaran, jadi ada semacam teori, jadi bahwa tekanan yang kita berikan terhadap oli ini itu sedapat mungkin itu akan memberikan efek yang kurang dari berat pierheadnya ini. Jadi misalnya ini ada pierhead 500 ton. Jadi tekanan ini harus kita berikan sekitar 80% terhadap berat 500 ton ini. Jadi mungkin sekitar 400 ton lah. Kenapa? Tujuannya biar ada semacam gesekan. Jadi masih ada semacam sisa berat daripada pierhead ini, sehingga masih ada gesekan pada saat pemutaran ini. Tujuannya adalah untuk safety. Jadi ini yang selalu kita lakukan. Kita tidak perlu memberikan tekanan terlalu besar terhadap Sosrobahu ini, karena itu akan membahayakan pada saat pemutaran. Jadi sebetulnya kalau kita lihat ini secara umum, kenapa Sosrobahu ini bisa menimbulkan? Itu sebenarnya sangat simpel. Mungkin kita tahu hukum Pascal. Jadi hukum Pascal itu menyampaikan bahwa tekanan yang diberikan pada suatu fluida dalam ruang tertutup itu akan diteruskan sama besarnya ke segala arah. Jadi dengan teori itu, pada saat kita berikan oli di inlet terhadap Sosrobahu, itu dia akan memberikan daya gaya ya ke atas itu sebesar luas dari Sosrobahu ini. Jadi bayangkan kalau kita memberikan katakanlah tekanan 50 kg per senti kalikan lebar dari luasan dari Sosrobahu ini akan menimbulkan gaya ke atas yang sangat besar, dan itu hampir sama dengan berat dari pierhead. Jadi sebetulnya sangat simpel teori Sosrobahu ini. Kita hanya menggunakan hukum Pascal. Kemudian pada saat penarikan ini juga sangat simpel. Jadi berapa sih gaya tarik pada saat ini ini kita tarik, kita putar, kemudian pasti akan menimbulkan momen tentu saja ya, karena kan biasanya pada saat rotasi ini kita tarik di ujung daripada pierhead, jadi lengan itu akan menimbulkan momen. Kemudian itu adalah fungsi daripada gesekan ya di Sosrobahu itu sendiri. Jadi meskipun tadi ada oli, tapi seperti yang saya sampaikan masih ada sisa. Kita harapkan nggak gayanya tidak sebesar daripada beban pierhead, jadi masih ada semacam gesekan di situ, dan itu akan merepresentasikan berapa sih tarikan yang diperlukan pada saat kita melakukan rotasi. Kurang lebih seperti itu. Ini adalah bagian akhir.
Pak Dodi,
ya.
mohon izin Pak Dodi. Iya, mungkin bisa diselesaikan 2-3 menit Pak Dodi. Setelah itu
Siap.
kita akan jawab. Terima kasih Pak.
Siap Bu. Terima kasih. Ini ada bagian akhir daripada Sosrobahu. Jadi setelah tadi kita melakukan rotasi, ini adalah bagian akhir, adalah kita menyatukan kembali antara pierhead dan kolom. Dan ini ada beberapa cara. Ini tergantung desainer ya. Jadi yang pertama adalah menggunakan Justran, kabel ducting, kemudian juga dowel ya. Bagian dowel kita lihat di sini ada ini adalah gambar di Cimanggis Bitung. Ini ada dua juga, ada Justran, kemudian ada dowel, kemudian juga kita lakukan di Filipina. Ada dua komponen yang menyatukan, dowel dan Justran. Ini adalah yang kita gunakan juga Sosrobahu. Ini saya balik ke sini, keuntungan. Jadi kalau secara umum, keuntungan Sosrobahu ini yang pertama adalah mengurangi dampak kemacetan selama konstruksi. Jadi dengan lebar luas lahan konstruksi nanti sempit, ini sangat membantu untuk mengurangi dampak kemacetan selama konstruksi. Kemudian juga waktu pelaksanaan lebih cepat, ini sudah pernah kita proof juga. dicapai, kemudian juga di Filipina ini waktu bisa lebih cepat. Terakhir ada keuntungan ekonomi ini yang selama ini mungkin tidak kelihatan ya, jadi dampak dari berkurangnya kemacetan itu akan memberikan keuntungan ekonomi yang besar terhadap stakeholder daripada konstruksi itu sendiri. Ini mungkin nanti kita sampaikan kalau ada pertanyaan. Ini salah satu cita angkatan adalah yang mempunyai license untuk menggunakan Sosrobahu. Terakhir sebelum kita akhiri Bu, saya ada quote di sini, adalah bangsa yang besar adalah bangsa yang menghargai hasil karya anak bangsa sendiri. Mungkin itu Bu Yureana, terima kasih. Mudah-mudahan bisa memberikan manfaat buat kita semua. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Terima kasih banyak Pak Dodi. Paparannya sangat menarik. Saya langsung saja ya Pak untuk
Silakan, Bu.
pertanyaan. Ya sudah ada pertanyaan dari ya. Jadi menanyakan tentang resiko gempa saat konstruksi. Ini bagaimana memperhitungkannya, begitu Pak Dodi. Silakan Pak.
Iya, jadi gempa ini sebenarnya sudah diperhitungkan Bu oleh desainer. Jadi pada saat kita membangun ini ya, membuat dengan menggunakan teknologi Sosrobahu ini, nah, itu yang membuat makanya kemudian rata-rata dimensi yang digunakan di kita itu cukup besar, terutama untuk pierhead dan kolomnya dibanding dengan digunakan di Filipina. Jadi di Filipina itu kita hanya dengan lebar yang mungkin hampir sama, sekitar 27 meter, itu berat daripada pierheadnya hanya sekitar 350 ton, bandingkan dengan yang kita gunakan di Japek. Japek itu hanya sekitar 2x2 ya, atau 4 lin. Itu lebarnya 20 meter lebih sedikit lah ya, mungkin 22 meter. Itu beratnya hampir 500 ton. Jadi itu yang membedakan ya antara kita dengan di luar gitu ya. Tapi memang itu sudah diperhitungkan oleh desainer ya pada saat mendesain ini. Tapi pada saat dia sebelum diputar, nah ini yang menarik, sebelum diputar ini sebetulnya kan bagaimana kita menanggulangi seperti gempa ini. Pada saat sebelum diputar ini kita tidak akan melepas semua supporting daripada PhD ini ya. Jadi seperti tadi gap dilatasi itu hanya akan dilepas sesaat sebelum dia pemutaran rotasi. Kemudian juga semua supporting ini tidak akan dilepas sebelum dia tepat sebelum mungkin katakanlah 2 jam, 1 jam sebelum rotasi lah ya. Jadi itu mungkin bisa menjawab pertanyaan terkait dengan gempa tadi.
Baik, terima kasih Pak Dodi. Kemudian pertanyaan berikutnya ini berkaitan dengan biaya dan juga waktu. Lebih efisien mana dibandingkan dengan sistem cantilever kotak, atau mungkin ada juga yang menanyakan ini Sosrobahu dibandingkan metode segmental, mungkin seperti itu, dan biayanya tadi Pak, mungkin satu pilar itu berapa mungkin ya. Terima kasih Pak.
Ya, memang belum pernah ada penelitian yang lebih detail terhadap ya, mungkin terhadap membandingkan biaya ini. Tapi mungkin bisa saya sampaikan. Kalau saya lihat memang mungkin kalau secara kita hanya melihat biaya konstruksi, ya komponen-komponen yang ada dalam Sosrobahu. Yang pertama kita harus untuk Sosrobahu, tetap kita harus menggunakan Sosrobahu, which is itu ada cost-nya, ada biayanya. Kemudian juga setelah itu kita putar, itu ada bagian konstruksi tambahan untuk menyatukan lagi antara pierhead dan kolom seperti tadi yang saya sampaikan, Justran, kemudian dowel dan sebagainya. Dan itu mungkin akan membuat biaya konstruksi sedikit lebih tinggi dibandingkan metode lain. Tapi yang kadang-kadang kita lupa itu tadi sudah bagian dari pertanyaan sebetulnya masalah waktu, Bu. Jadi waktu ini akan sangat penting, dan pengalaman kita dengan Sosrobahu ini lebih cepat. Jadi pengalaman kebetulan seperti di Filipina, kita sebagai investor, waktu akan sangat sensitif. Jadi kalau saya hanya berpikiran bahwa oke, biaya konstruksi lebih tinggi, saya menggunakan metode lain, tapi dengan waktu yang lebih cepat, seperti kalau kita membangun jalan tol, otomatis kan waktu akan sangat sensitif ya. Jadi begitu kita waktu secara cepat, lebih cepat, kemudian bisa kita buka, itu juga akan sudah menghasilkan revenue gitu ya. Jadi kalau secara secara keseluruhan, kalau kita melihatnya sebagai stakeholder lain gitu ya, itu akan menguntungkan. Itu dari sisi tadi kita bicara mengenai waktu dan biaya konstruksi. Kemudian keuntungan yang tadi kebetulan belum saya uraikan lebih ini. Kita pernah menghitung pembangunan jalan ini kan sebenarnya stakeholdernya banyak. Tidak hanya mungkin kontraktor, investor, tapi juga masyarakat sekitarnya yang terdampak daripada pembangunan ini. Seperti kalau kita lihat jalan tol Japek misalnya, seberapa besar kerugian masyarakat yang ditimbulkan akibat kemacetan yang ada. Dan itu kita pernah menghitung gitu ya, berapa sih keuntungan kalau kita menggunakan Sosrobahu. Dan itu cukup besar karena dampak ada dua komponen ya. Yang keuntungan didapat. Satu, yang jelas kemacetan, itu bisa kita kurangi dengan metode ini. Yang kedua, dampak daripada kemacetan ini, biaya operasi kendaraan daripada pengguna jalan yang terdampak itu akan juga berkurang gitu ya. Yang ketiga adalah waktu. Jadi berapa besar waktu kita yang hilang akibat kemacetan ini gitu ya. Jadi kalau kita hitung secara keuntungan ekonomi ya, meskipun mungkin tadi biaya konstruksi sedikit lebih tinggi, tapi keuntungan ekonomi seperti pengurangan kemacetan, kemudian biaya operasi kendaraan, waktu dan sebagainya itu sudah sangat ini ya, sangat efektif untuk mengcounter tadi biaya konstruksi yang mungkin sedikit lebih mahal. Apalagi kalau kita sebagai investor, kalau ini bisa lebih cepat kita buka, katakanlah 3 bulan, 5 bulan, wah sudah cukup memberikan revenue yang lumayan. Begitu kira-kira, Bu.
Oke, baik Pak. Mungkin ini terakhir saja, singkat saja. Masih banyak pertanyaan sih Pak. Mungkin Pak Dodik mungkin bisa juga menjawab di Q&A ya. Kalau bisa nggak ya panitia ya, mungkin bisa menjawab di sana. Atau mungkin terakhir ini tentang pertanyaan kegagalan, apakah pernah terjadi dalam pengerjaan, kemudian seperti apa penyebabnya, kira-kira kemudian apa namanya, mungkin apa tadi ya, Sosrobahu ini tahan berapa lama? Mungkin itu singkat saja Pak Dodik.
Ya. Oke, mungkin saya jawab pertanyaan terakhir dulu. Sosrobahu tahan berapa lama? Jadi Sosrobahu ini seperti yang tadi saya sampaikan adalah hanya alat putar. Jadi artinya begitu ini sudah memutar pierhead, tugasnya selesai. Jadi dia akan tinggal di situ, olinya juga kita keluarkan. Jadi sudah selesai. Jadi itu semacam mungkin besi ya, rebar begitu ya. Jadi tidak ada fungsi struktur dari Sosrobahu karena fungsinya hanya sebagai alat putar. Jadi berapa lifetime-nya ya seumur hidup karena tidak ada fungsi lain selain alat putar gitu ya. Itu konsepnya seperti itu. Kemudian mengenai kegagalan, jadi memang so far kita katakan tidak ada kegagalan, tidak pernah ada kegagalan karena memang kita menggunakan konsep bahwa ini adalah zero tolerance. Jadi kita harus melakukan dengan benar-benar hati-hati. Ada SOP yang harus kita lakukan. Jadi setiap kali SOP dilakukan ada semacam checklist apakah ini sudah benar atau tidak begitu. Jadi tidak pernah ada kegagalan. Cuman memang ada beberapa kasus yang timbul bukan karena Sosrobahu tapi karena pekerjaan lain. Seperti saya tidak perlu menyebut proyek apa, tapi ada satu proyek di mana kolomnya itu tidak simetris ya, tidak persegi, jadi antara lebar dan panjangnya beda. Jadi pada saat dicor pierhead-nya sebelum diputar, karena yang di sisi yang dicor ini kolomnya lebih pendek ya, ini pada saat periodnya dicor itu ada semacam penurunan periodnya. Jadi mungkin karena slipernya yang di bawah dari period kurang bagus begitu ya. Jadi istilahnya periodnya turun lah. Karena tadi kolom panjang dan lebar tidak sama pada saat diputar itu dia terjadi gesekan sehingga tidak bisa diputar secara penuh. Dan solusinya apa? Ya solusinya kita harus chipping lagi, kita benarkan periodnya karena memang pada saat pengecoran period tidak dilakukan dengan benar gitu ya. Jadi rata-rata seperti itu. Jadi bukan karena kasus Sosrobahu tapi karena pekerjaan lainnya yang tidak dilakukan dengan benar. Ada kasus lain, ini cukup banyak sebetulnya terutama di kita di Indonesia karena Sosrobahu ini juga bisa kita lakukan untuk period yang unbalance. Jadi antara balance antara berat sebelah kiri dan kanan atau kalau depan dan belakang istilahnya atau kiri kanan yang tidak sama. Itu akan menyebabkan unbalance dan konsep Sosrobahu ini harus balance. Jadi pada saat pemutaran ini harus balance dan itu harus bagaimana bisa balance itu kita memberikan counterweight. Dan ada beberapa kasus di mana counterweight yang dilakukan itu pemasangannya tidak sesuai dengan perhitungan. Nah itu yang menyebabkan ada semacam pada saat pemutaran ini ada semacam gesekan karena pemasangan dari counterweight tidak sesuai dengan perhitungan sehingga menyebabkan unbalance-nya masih ada meskipun kecil. Itu menyebabkan pemutaran sedikit lebih susah karena masih ada gesekan di situ. Mungkin seperti itu, Bu.
Baik, terima kasih banyak Pak Dodik karena waktunya ini sudah sampai pada akhirnya. Saya mengucapkan banyak terima kasih untuk Pak Dodik. Pertanyaan ini sebenarnya masih banyak, akan dirangkum oleh panitia dan nantinya mungkin bisa disampaikan ke Pak Dodik ya Pak, bisa untuk memberikan jawaban atas pertanyaan ini. Mudah-mudahan. Ya, terima kasih. Sampai ketemu lagi Pak Dodik. Kalau ingin terus mengikuti webinar ini, dipersilakan.
Ya, terima kasih sekali buat semua, buat Binus. Mohon izin kami akan live sebentar. Terima kasih.
Terima kasih. Thank you so much, Pak Dodik Marseno.
Thank you.
Now we would like to move to next presenter, Bapak Gary Djojo. He is a senior structural engineer of Harris Foster Consulting Group. So I would like to invite Pak Gary. So he is a Ph.D. in civil engineering from University of Auckland, Bachelor of Engineering from Parahyangan Catholic University. This is a short CV of his work experience, collaborator with the New Zealand Ministry of Education on the development of new classroom blocks for public schools across the country. Also, he worked on prestigious commercial buildings in Indonesia and New Zealand, including Central Park and Kota Casablanca in Indonesia, as well as luxury apartments and retirement villages in New Zealand. Welcome, Pak Gary Djojo. Please share your PPT and the time is yours. For the participants, if you have questions, you can write in the chat box or in a Q&A or raise your hand. We'll open the Q&A after Pak Gary finish his presentation. Pak Gary, you have 35 minutes, maybe until 12, around 12:15 or 12. Oh, 5 minutes to 12. Yes.
Okay. Thank you. I think it's better for me to. All right, I'll set up first. I believe that everybody can hear me.
Yes, we can hear you very well.
And you can see my screen as well.
Yes.
All right. So, yeah, thank you, Ibu Yureana and MC Engi and Binus. My name is Gary Joyo. Today I would like to present actually this was my PhD research at Auckland Uni. The name is Low Damage Design for Steel Structure, namely the centralized rocking concentrically braced frame. So I work with Charles Clifton and Rick Henry here. So these are my supervisors at the time. All right. So I think before we talk further about the centralized rocking concentrically braced frame, so it's better for me just to refresh like how do we usually design. So it's easy to describe with chain analogy. If you have a chain and then after that you pull that, and if these are having the same capacity, so basically it will snap and there will be a brittle failure. This kind of failure is the thing that we want to avoid. Because during the earthquakes, then it will be a disastrous failure. So that's the reason why engineers design with the ductile link. So even though you have two brittle links here, if you have one ductile links, then if there is an earthquake, or if you pull out the chain, then the ductile link will elongate and will yield. So that gives us more time for person or for people from the buildings to escape. So this is something that we adopt in our structural design for concrete buildings, steel buildings, or timber buildings. So I'll give you the example here. So this is a 3-story moment resisting steel frame. It was shaken by Sendai. It's in Sendai, and it was shaken by Tohoku earthquake. And the second one is the 26-story reinforced concrete structure with shear walls. It was shaken by Christchurch earthquakes. So we can, on the next slides, we can see like the behavior of each building. So if you look at the steel frames, normally the hysteresis response will be something like this. So in this X direction, it will be a lateral displacement, and the Y direction is the force. So if you look at the pattern here, if there is a loading here or seismic loads, then it will create a line like this, and this is a cycling back, and it will be going under the seismic event, and eventually it stopped here. But when it stops here, so basically there will be a lateral displacement. So if you can see, then this building is not centered back to the original position. This one is for the reinforced concrete structure, and this is something that you will expect. I know this one is, well, everybody knows that the performance of the steel structure will be better than concrete. That's the reason, this is the reason. So basically, if you look at this, the loading and the unloading here, it will degrade it, and eventually it will stop here. So even though like that, so this one still meets the life safety performance, meaning if there is people in the building, people can escape, and then the building didn't collapse. But the only thing after this, so the building cannot be reused immediately, and then there will be like so many inspection, and probably a demolition may require. So what if we have a structure with the hysteresis response like a flag shape like this? So basically, if there is a force here, and then when it unloads, then it will return to the original position. That's the reason why I create in this research, I created centralized rocking CBF here. So with this, then we can say that we can have an immediate occupancy performance level. So the idea is after the earthquake, maybe a simple inspection, and I've already put that the weak links or the thing that need to be inspected, and that's if we inspected that and it was fine, then the building can be reoccupied immediately. So if we come back with this analogy, so how about if we provide a spring here? So when we provide a spring, when you pull up the chain, then the spring will spring, and then after that it will spring back if you unload it. So the way that we create the flagship hysteresis analysis is hysteresis curve here. So basically, it has a spring system. So basically, it's something like a rubber here. If you can see this, that's the easiest for me to present to get the analogy. So if you pull that and you release that, then it will come back to the original position. So that's the way that it will bring the structure back to the original position. But if we just want to rely on that, so basically the building will just like shake or rock, something like that, and then it will never stop. That's the way that we need to have an energy dissipation. So the energy dissipation curve, it should be something like this. It can be from friction, it can be from anything that can dissipate the energy. If we combine two of these, then it will create a flagship hysteresis curve like this. So if we look into further on the centralized rocking CBF here with double acting ring springs, I have collector beam, brace, concrete filled square hollow section columns. And then these are the key features, the double acting ring springs and the rocking pivot. And how do I place this into a structure? So this is a floor plan that I created. So for this example, I've put 2 at the perimeter and 2 at the middle. One thing that maybe I need to let you know, there is a bit difference between the design in Indonesia normally and the design in overseas. So basically in Indonesia, we are usually using concrete moment resisting frames where all base will resist seismic forces. But in this case, because this is still structure, so we can design for this column and that column to be only resisting gravity. So it can be designed as flexible as it can be. So the seismic loads will be attracted to the brace frames here. That's the reason why we can just check this brace frame under seismic force. So for the performance objective that we will discuss to make sure that this can be implemented in the real building is, one is the serviceability limit state earthquake or wind loads. So we don't really want to have a system that will swing during the SLS earthquakes and wind loads. So the system needs to be remaining elastic and stiff. And under ultimate limit state earthquakes, then the system commences to rock, but all members remain elastic, and the double acting ring springs dissipate most of the earthquake energy and provide self-centering after an earthquake. And under maximum considered earthquake, MCE, then when the double acting ring springs are at the maximum level, the threaded rods and column-based plates are expected to yield. We can discuss this later. And the column, the collector beams, the braces will remain elastic to prevent any collapses of the structures. Then it will come back to the original position after an earthquake. This is the way that we make sure that we achieve the immediate occupancy performance level. So one of the key features in this CRCBF is ring feather friction ring spring. It is a compression only spring comprising inner and outer spring. So I have the spring here. So that's the ring. So we just stack this. And when you compress, then it will be a spring. And it has a constant and stable force displacement relationship. And the equation is quite simple. Force over displacement, that's the stiffness. And it can be pre-stressed up to a defined force level. In this case, for example, 50%. So say like if you have 100 kilonewton spring and you preload it up to 50%, that's 50 kilonewton, then any loading below 50 kilonewton will not make the spring to compress further. So that's the way that we make the design of SLS and the wind loads level. And 2/3 of the energy will be dissipated, and 1/3 of the energy will be stored and elastically restored to the released to the on the unloading here. And then the ring springs can be arranged in series and parallel arrangements. So if you stack more, then it will create more displacement. And if you have a bigger spring, then it will give you more capacity. So these are the equation. So we now look into the double acting ring springs that I created. So I have column here, and that's the column base plate. And I have a spring cartridge here, and the ring spring is inside the cartridge, and there's a threaded rods. And if there is compression force, then it will compress the column base plate, compress the top plate here, compressing the ring spring to the foundation. And then if I unload it, then it will come back to the original position. And if I have tension force, then it will lift up the column here, lifting up the column base plate, lifting up the threaded rods, compressing the ring spring, and then transfer to the cartridge here, to the foundation. So in this case, even though ring spring is just only compression spring, but it can be utilized as the compression and tension. So that's the way that we call it double acting ring springs. So with this kind of system, we can have this flag shape hysteresis response. That's the way that we want to make sure that the building can return to the original position. And my other research is about the connection here. So basically, the connection here is not, there will be an eccentricity between the beam and the brace. And because we concrete filled this, so there will be like a diagonal compression strut and tension tie. And that's the way that the force is transferred from the beam to the brace and the column. Under compression, and there will be a diagonal compression strut here, and the brace will be in tension, the column will be in compression. But this will be like another session, so I'll just give you a brief explanation of this. And the other key feature is a central rocking pivot. This is really important because all the gravity loads will be resisted on the central rocking pivot here. And during the earthquakes, then it allows to rock back and forth like that. And this also responsible to transfer in-plane seismic base shear and to maintain the in-plane stability of the CRCBF. And if the earthquakes is larger than what we designed, so this is something like a structural fuse, a fuse mechanism. So if there is something, if there is a force that's larger than what happened in the earthquakes, then this area will stretch out. And then if that stretches out, then it can be, because that's a threaded rod, so it can be easily replaced. And the second one is, if there is like a large compression, then the column base plate will deform or yield something like this. This can, to do the remedial works on this, then you can just try and straighten that up after an earthquake. So I did the structural analysis just to make sure that my design concept is working on the desktop, on the computer, before I'm doing the experimental testing. So I created this structure in SAP 2000, and I believe that SAP 2000 and ETAPS is just having the same menu and same engine, analysis engine. So yeah, both of them can are workable. And this is the member sizes that I applied. And ETAPS and SAP 2000 have a feature of modeling the ring spring. That's the, we can assign that as the damper friction spring. So we can input the spring stiffness and the spring displacement here. So we go to the experimental testing now. So before I do the big testing, so I'll try to start to test the critical component, which is the threaded rod, because this needs to yield in this region. That's why we create something like this. It's a machine down threaded rod. So we can expect that the yielding will be in this region only, not breaking up the threaded rods, the thread here. So when after the earthquakes, then you can just simply undo it and you can put back the threaded rods. So this is acting like structural fuses. So I have two types. One is with the 21 millimeter diameter of shank. And I used this on my first double acting ring spring testing. And the bigger one I use for the full assembly, sub-assemblage testing. And this is the mechanical properties. So it meets the requirement. There's a bit lower than the standard, but I think this is still acceptable. And we move to the double acting ring springs. So as I explained previously, so this is the double acting ring spring that I tested. So I loaded 3 times with the uniform cyclic loading here. And what we get, so we have a stable and repeatable hysteresis curve here. If we compare with the catalog from the ring spring, then it just gives me like exactly what they have in the catalog. So there is no strength degradation, there is no stiffness degradation. And this is the testing. So I'll give you a video here, my testing about the double acting ring spring. This is a time-lapse mode. All right. So yeah, so after that, we know that it works. So we try to put that into a bigger sub-assemblage testing, which is this one. So I know that we can't, well, because of the limitation of the test hole, so we can't erect like 4-story high. But I think we agree that the critical parts will be like at the bottom story. And because this one is symmetrical, we can just have like half of this to be tested. And we can assume that on the other side will have the same response or behavior. So this is a double acting ring springs, and this is the rocking pivot. We need to know about the global behavior of the CRCBF. That's the reason why we do the testing here. And the rocking pivot under the static and the dynamic loading. And also because this one will create an arc during the rocking. So we need to know the behavior of double acting ring spring movement. And lastly, we need to check the internal forces, and we compare with the computer analysis that I've done previously. So there are so many strain gauges here to give me the results. Similar to the double acting ring springs, so I applied uniform cyclic loading first to get to know the behavior, whether it behaves well and as our expectation. So we apply a slow cyclic loading. It's about 0.5 millimeter per second, 3 times, and a little bit faster, 20 millimeter per second here. And then after that, after we're confident with the static loading, then we apply a dynamic loading. So this one was taken from El Centro earthquakes. This was generated from my structural analysis from level 1, lateral displacement. Then I input that into the actuator and we'll see what's the behavior of the sub-assemblage. And this is the test result. As you can see, like there are 4 different type of loadings here, but as you can see that it's still repeatable and it's consistent between one testing and the other testing. And I test this here more than 50 times, and still like I'm having the same hysteresis response here. So even the dynamic one, we also still have the same response here, which is good. The only thing is just if you notice there is a bump here. So basically during the testing, when it compressed, so it tilt a little bit because I just only have the guide rail on the side. But in the real building, because there is a structure connect perpendicular to it, so this will be transferred to the other CRCBF on the perpendicular to it. Yeah, so this is the testing that I do. So maybe we can check together here. So I input the El Centro earthquake record here, and then the actuator is pushing back and forth here, and there is an LVDT here. And then we can view this one more time, but this one is it's more detailed. So you can see the hysteresis response on the right top corner here, and the double acting ring springs on the front view on the right bottom corner here, and the rocking concentrically braced frame here, and then the side view of the double acting ring spring on the bottom left corner here. Let's see it together. So as you can see from the diagram here, so it's quite stable, and then it's repeatable and consistent between one testing and the other testing. And lastly, it returns to the original position. So after the testing, I inspected all the critical parts. So I didn't see any yielding or damage on these structures. Only thing, I think this one, if I remember that it stretches out a little bit because it creates an arc. So the further of the double acting ring spring, it stretches out a little bit further. So that's the reason that this stretches out a little bit. But in terms of the testing, there were no strength degradation and stiffness degradation. So it always formed a flagship hysteresis curves. So we need to be realistic here. So I compared this with the well-known base isolated system because my system is quite new. So I can say that it's a new rocking system for the CRCBF, while the high damping rubber bearing, it's a well-known base isolated system. Both of them are expected to have immediate occupancy performance level. Both of them actually developed in New Zealand, but base isolated system is quite popular in Japan. Ring springs are only installed at the location of the CRCBF. So basically there are 4s, and 4 times 2, then 8. But for the high damping rubber bearing, you need to put on all or every column, so to make sure that it can slide during the earthquake. CRCBF, I believe that's having a low or no maintenance because it has, the material is high strength steel compared to rubber, because you need to have maintenance for rubber. CRCBF, so far it's used for regular buildings, and I understand that base isolated system have more flexibility on the building. So any type of the buildings, you can still utilize that, because the idea is just it slides during the earthquake. And the CRCBF is also used for the low-rise buildings. The most benefit one, it has a good design procedure, which have been developed with the New Zealand standard, while the base isolated system, there is no really well or comprehensive design guide. I know that a few got it from the US or Japan, but still, like, it's still not easy just to apply that into the structural analysis. I also must admit that there are challenges to implement a new system, even though in New Zealand, but it's getting more and more. One is the structural detailing and interaction between structural elements. So we need to have like a comprehensive QA internal meeting to make sure that everybody understand what we're doing and we're on the same page. And we need to have a competent peer review as well. It's a little bit challenged if the peer review is just at the first time saying that, no, we can't use this system because I don't want to use this system or something like that. So it will never happen to be built. And we have the university reviewers as well. That Charles Clifton is from Auckland Uni. He was my supervisor, and Gregory McRae from University of Canterbury. And also the non-structural detailing, because if I make like a great building, it will never collapse under earthquakes, but then the sprinkler, which maybe didn't allow like a large displacement or something like that, and the pipe is broken and the water burst, and basically you need to recarpeting, you need to redo the internal or the interior, and that's also like another cost that we need to think about. And also because the ring spring was usually used for mechanical engineering. So basically, it's the size of the ring that's available until now. It's not for the building, but they have a bigger size here. But we need to ask them to make it for the oversized ring springs. You have the contacts here, Lars Jahnel and Ude Kramer, so you can contact them. But the only thing is probably the price or the cost of the ring springs may be a little bit expensive because it's non-standard ring. And to conclude this, based on the testing here, we can say that the testing went well. The CBF with axial forces resisted by ring springs under the columns and the shear carried by a central rocking pivot has been presented. And we know that the double-acting ring springs provided stable and repeatable hysteresis behavior in tension and compression, independent to the loading rate. During the rocking, we understand that the ring spring on each side had different displacements, which we can take into account that's in the design. And the pass-through beam-braced column connection from tension and compression struts to transfer lateral loads from the collector beam to the brace and the column. And lastly, based on my testing, the CRCBF system behaved well with the frame remaining elastic and return to the original position after the loading is completely finished. This is my last slide. So the application of the low damage design is not only about the rocking structures. So this is one of the things that maybe people just maybe misinterpret this. So low damage design need to have a device or something like that. So it's not. So if you design a building with the elastic systems, mu here is comparable to R system in Indonesia. If you haven't changed in the code, so I think it was R system. So we need if the building it designed on the elastic system, so that's also a low damage design. So the R system here, if I'm not mistaken, my mu equal 3 is comparable to R equal 5 and mu equal 6, which is the highest in New Zealand, but we never go up to that level. It was comparable with R equal 8.5. That's ductile. And we have another option where there is a sacrificial system. So basically this is a sliding hinge joint. So basically under the earthquake, the joint will be flexible, but still can transfer lateral forces. And then after the earthquake, because there is an optimized here with the Belleville spring, again spring, so it will bring back the building into the initial position. And there is another one here, a replaceable active link EBF. So the idea is after the earthquake, so if the EBF active link here yield, so basically they can just replace this and the building will be able to be occupied immediately. And this is the rocking system. This is similar to what I developed. So basically we have springs here at the edge of the walls. And then there's a, the dissipation is based on the friction. And this one, there is a post-tension tendon inside, which is acting like a spring. And this is the energy dissipation. And this is the famous high damping rubber bearing. This was taken from GGT in Jakarta. That's Gudang Garam Tower. And this one is a single pendulum bearing. I think this was used for the new Apple campus in the US. Okay, I think that's all. Thank you for this. And if there are any questions, I'm happy to answer it.
Thank you, Pak Gary, for a very nice presentation. So shall we start the first question? I think it's from Pak Junata Lim. So he is asking how to model a friction damper or spring in software that doesn't have specific feature for it.
The software needs to be a nonlinear because you apply a nonlinear spring. Secondly, if there is no feature, then probably there is like a force displacement input, then or maybe under the link or spring that at least you can input the force and displacement. Then you can recreate that the spring force displacement that I have into your program. So maybe if I can come back here. Did I? Yep. Yeah. If you can see my screen here, so this has been tested, and the hysteresis curve is something like this, a flag shape hysteresis curve. So if your program have an input of the force and displacement or a spring input, so you can just model this. And this one is one third of the spring capacity. So you can model that by yourself.
So that's the approach that we can do in the software, Pak Gary.
Sorry, could you please repeat?
So that's the approach that we can apply in the model.
That's correct.
Okay.
Yeah, but if you're using SAP 2000 or ETAPS, there is friction damper under the link or spring that you can utilize. So you simply just choose the spring and choose this friction damper, and you input the values. The input's still the same, like that's the length of the displacement and the capacity, the spring stiffness. And it can be calculated manually, and then you input that, and the building will behave according to the spring that we input.
Okay, thank you so much, Pak Gary. It's a second question from Pak Mejamin. How to calculate this in a three-dimensional analysis?
Good question. Yes, so this is the structural analysis that I use. It's SAP 2000, so it's a three-dimensional analysis. But the way that the brace acting is one way. So that's the thing that we need to make sure that the frame on this direction is flexible. So it will not generate like bidirectional loading. But if you ask about the three-dimensional model, so yes, we can model that in the three-dimensional structural analysis package. And this is what, as I mentioned to you, this is the spring that I input, and that's the spring stiffness that I input according to that that's hysteresis curve.
Okay, thank you, Pak Gary. Pak Mejamin, hopefully this answer your question. Next question is maybe about the maintenance. Pak Gary, you mentioned about the comparable between the rubber spring and this material, the CRCBFs. And so actually, is it really zero maintenance? I mean, are there still monitoring the system, this project during the lifetime of the building? So can you give us maybe the experience from the previous installation of this technology in the buildings so far?
Yeah, so I believe, because I haven't done this in the real projects, but I believe this is low to no maintenance because the material is spring. The material is steel for the spring. And if you look at this, the window here, it's not a window. In the real building, we don't need to have a window here. This window is just only to show how the spring will work. And because of that, so it's concealed in a cartridge in the safe place. That's a good question, but I talked to German people, that's German engineer, and they're really strict on this. They said that this will be no maintenance as long as you can maintain the grease, because grease will attract the dust and it will, I can't really say alter the behavior, but maybe it will just reduce, or it will be slightly make the behavior a bit different, but not in general. So as long as you can protect from water or dust, and make sure that the grease is still intact with the rings, then he believed also no maintenance required. Oh, also don't place that at the lower base or something like that, just to make sure that if there is a flood, so the water will not like go into the to the cartridge. So maybe you need to lift that up a little bit on the, say, like above the ground.
Okay, okay. So is it more complex to apply this to in the design of the building? Will it be adjustment or maybe during the design of the building? So how do you think about applying this to general design of a building?
In terms of the CRCBF itself, I'm pretty sure that it's final, so it will behave what I tested, and I've loaded that many times, and I've already applied different earthquake records. So as long as it's within the capacity or the loading or the design of the CRCBF or the double anchoring springs, I believe that it will perform well. The only thing is just, this is not just about the brace itself. It has another structures like the secondary beams, the floor. So we need to accommodate during the rocking. We need to accommodate that to make sure that the floor will not break during the rocking, because floor is also important to transfer the lateral force to the CRCBF. And that's the thing that probably we need to look into the detail. And the other thing is, as I mentioned to you, it's services. Sometimes like services came later after the design have been completed. And after that, services just ask for penetrations on the beam. And then somehow when we design that, we can't have, say, 200 millimeter penetrations. And then somehow like the surfaces still put the pipes without allowance or tolerance. And during the earthquakes, because it will rock something like this, then in another part, probably it will break the sprinkler, and the sprinkler pour the water to the floor, and also that's also costs you a few few dollars. So it needs to be like discussed with the other discipline as well, and the architects as well. So basically, because it's rocking, so we need to have a cladding which can accommodate that rocking. Maybe we need to have a slotted joint on the mullion. So that kind of thing that we need to discuss further. But back again, so if we look into the brace itself, I believe it will perform well under earthquakes, and it will behave with the flagship hysteresis curve and will return to the original position after an earthquake.
Okay, thank you so much, Pak Gary. Maybe we come to the end of this Q&A. So if I may conclude, so maybe the proper engineering and design, as well as regular inspection and maintenance are essential to ensure the functionality of the CBRF-BFs and its effectiveness in earthquake mitigation. Okay, thank you so much, Pak Gary. So we come to the end of this session, but I would like to remind you after the break, so after this, we will have 30-minute breaks for lunch and afternoon prayer for the Muslims. So we will start at 12:30 for the third presenter, Pak Albert Lim Lum Kong, the Senior Geosynthetic Manager at Solmax. So I will see you all at 12:30. Once again, thank you so much, Pak Gary Djojo. See you soon.
Thank you.
Thank you.
afternoon, everyone. The webinar will be starting soon, and we would like to invite you to join the next session. And for Dr. Yureana, you can take over again for the next session.
Okay, thank you, Anggi. We will start the third presentation for today's webinar soon. Good afternoon, Mr. Albert Lim.
Yeah, good afternoon.
Shall we start our session for your presentation?
Yeah.
Okay, allow me to read your short CV. So good afternoon, everyone. So our third presenter is Mr. Albert Lim. He is a senior geosynthetic manager at Solmax. His education background is a Master of Science degree from University of Mississippi, USA. This is a few of his works experiences. So at this moment, he's a senior geosynthetic manager at Solmax. Previously, he's a collaborator at National University of Singapore, Nanyang Technology University, and Monash University. Also, he is an author and co-authored of more than 30 international and local technical papers. So let's Mr. Albert Lim to start your presentation. The time is yours.
Okay. Thank you, Yureana, and a very good afternoon to everyone. Yeah. Okay, let me share my slides. Okay. Okay, can see my slides?
Yes, very good.
Okay, let me see. Okay, a very good afternoon to everyone. So this afternoon, I will do a sharing on the use of geosystem for coastal engineering application. Okay, geosystem it can be formed on the land, and it can be formed in the water, and the field height, right, it can be around 1 to 2.5 meter. And normally we have hydraulic field, the geosystem in this case is a geotube with sand, yeah, or silty sand, and we will normally fill this to the maximum height or maximum density. So when we fill it, right, the sand slurry will be in the tube, the water will drain out from the tube, the sand will be trapped or encased in the tube. And with this, we form a mass gravity structure for hydraulic and marine condition. Okay, this is how a geotube looks like. Yeah, this one, the height, right, as I highlighted earlier, it ranges from 1 to 2.5 meter. The inflated height is filled with sand, yeah, or sand slurry. And normally when you pump, right, this is the sand slurry, you pump into the tube. The length normally is about 50.5 meter, yeah. And the water will drain out from the tube. The sand will be trapped in the tube. And you will repeat this process for the whole tube length. Okay, this is a normal, or I say a standard procedure for filling the tube. You will have a steel tank, and in the steel tank, you will put in your sand slurry pump inside here. And from there, you will pump water into the tube, and you got an excavator to excavate the sand and be put into the tank. And this sand slurry, 20% sand, 80% water, you will pump this sand slurry into the tube. This is the normal standard procedure. We use this for filling tubes. Okay, so where are geotube used? The normal application is for your building front, to protect your building front. Yeah, can be as a submerged breakwater or a low crest breakwater. It can be act as a groin, yeah, to protect your this beach front, and can be so-called for land reclamation. But in most cases, right, or in terms of applications, right, the biggest applications are for land reclamation. Here for land reclamation, the tube replace the rock core. Conventional way, you use a rock core, but in this case, what I'm trying to say is that you use the tube to replace the rock core. It's faster to construct. In terms of cost, is much more economical. And we can also use this to replace the breakwater. Like in Indonesia, the project, especially in Ancol, this for the land reclamation, is used to replace the rock core. So here, right, instead of using rocks, we use the geotube, fill the tube with sand slurry to replace the rock core. Okay, so for geotube design, is designed to the Dutch design manual, Cur 217, and this Cur 217 right now is translated to English in 2013. So in English is I mean, we can actually follow on the design. It can be used for design of bags, geotextile mattress, and tube. So the Cur 217, it can be used for bags, geotextile mattress, and geotextile tube. But for today, I will not cover the detail of design. I will just cover how we use the tube and where are the tube being used for critical projects. Okay, so the first project I would like to share is for this project in Vietnam. This is the Lac Huyen Bridge project in Hai Phong in Vietnam. In this project, we have to construct a so-called a bridge. This is the bridge structure. The length of this bridge structure is 5.9 kilometer length. Yeah, 5.9 kilometer length. And out of this 5.9 kilometer length, around 3.9 kilometers, we want to use the dry method to construct this pier for the superstructure. This here, because it's the deeper section, we use the offshore method. Here we use the so-called the dry method. So here, so what I'm trying to say is that I will use the geotube to form the coffer dam for your this bridge pier construction. Yeah, and as a geotechnical engineers, right, in this project we face challenges because the soil are very soft. The 4 distinct layer. The first layer, right, is very soft organic silty clay, about 5 kPa. Then around 6 to 8 meter is 10 kPa. So I can say that on average it's around 7.5 kPa for, I mean, the depth about 50 meter depth. Then after that it's only a stiff marine clay. So if we see from here, right, the top here is very soft marine clay. And this is basically, you also have bearing capacity problem, excessive settlement. Okay, so conventional way, you will actually use ship bow for conventional way. But if you use ship bow, right, I mean, because here is about 50 meter depth, it's very difficult to construct because especially it has to be 1/3 and 2/3 this embedded depth. So for ship bow, it's very expensive, it's very costly because this is in the tidal flat area. If you use the conventional rocks dumping, it will actually sink down, yeah, because it's very soft. So what we have done is that we actually use a geotube on the left, 3-layer geotube to form this height of about 4.5 meter, and 3-layer geotube on the right. And from there, we actually do the hydraulic field inside. And once that's been done, we use ship bow. When we do the excavation, this ship bow is only to prevent water seepage during the excavation. And then from there, we do the superstructure. This is how the geotube looks like. Yeah, these are filled with sand. Water will drain out. It traps the sand. And from there, it forms the structure over here. Yeah, so you want 3 layers on the left and 3 layers on the right, and you actually backfill. Okay, this is how we actually so-called, I mean, unroll the geotube at the project site. Yeah. So this is the amphibious excavator. Yeah, because it's a soft marine clay, as I highlighted earlier, it's around 7.5 kPa. This unrolling the geotubes, it floats in the water because the specific gravity is less than 1. Yeah. The length of the tube is 50.5 meter, the length. And once it has been you unroll out, we will actually anchor it in position. and from there, we pump the sand slurry into the tubes. Yeah, this is the seal tank that I spoke about. The sand slurry pump is in the tank. You flush water, put the sand inside there, and this sand slurry, 20% sand, 80% water, is pumped into the tube. So you can see from this type of method, right? I mean, you use very minimal workers. It's only the excavator and the sand slurry pump, and a lot of sand, a lot of water, and it suck the sand slurry into the tubes. Okay, so we can see that this is the first layer where the water drains out from the tube. The sand is trapped in the tube. It's highly densified because you use water pressure to push the water out from the tube, and it traps the sand. Layer number 1 over here, because we're going to pump to 4.5 meter. Okay, so as I highlighted earlier, because the sand is, the soil over there is very soft, and this is the tidal flat. So before we actually pump the sand, we have to actually tie the tube to the pole. So once it's done that, you start the pumping. This is the first layer, you pump. Then from there, you pump the second layer on the left. And this, in between this layer, you actually do hydraulic fill to form the coffer dam. Yeah, you can see from here, I mean, this is a 4.5 meter. This is above the tidal flat. And this is the superstructure already. It's up already. And from there, your heavy machinery can be actually sit on top. So what I'm trying to say is that the tube, right, you can actually design this to curve 217 to take the active or the surcharge from the heavy machinery and from the active earth pressure from there, and also from the soft boring clay. So there is a reinforcement under the coffer dam to take care of the slip failure. So this tube, right, are actually designed to have very high weathering resistance. There's no rock cover. No rock cover is required because we can design this tube to the design line of your superstructure. Yeah, you can see from here, this is finished construction. The tube still have to be there for the superstructure construction. Yeah, no rock is required from here, and this is completed already. So this is for the coffer dam construction for the Lac Huyang Bridge. Yeah, and it actually allowed vegetation to grow over the tube. This is in 2016, and this is in 2022. Okay, so from this the Lac Huyang Bridge, I will go to Deep Sea 2 project. This is also in the same area. So if you see from here, this is the bridge structure over here, Lac Huyang Bridge. Yeah. So this is under JICA ODA loan projects. They actually built the Lac Huyang Deep Sea Port, and due to this deep sea port, these bridges, right? There is a lot of activities for the so-called for the factory construction or the land development. This is Deep Sea 2A. These are using geotube to form the dike for your land reclamation. This is Dimbu, South Dimbu. These are also using the geotubes. And this is Deep Sea 3. Deep Sea 3, they also use the geotube to form the dike, yeah, for the land reclamation. And this is Queening over here. These are also using geotube. So you can see that this the geotube that actually it offer a very economical solution, especially you are in tidal flat area facing soft burning clay, because it allows you to do the dike construction for your land reclamation. Yeah, you can see from here, this is Deep Sea 2. These are using geotube. These are divided into 3 phases, and each phase is about around 3 to 5 years. This is phase 1, phase 2, phase 3. So with this type of option, right? Conventional way, you have to use rocks at phase 1. So when you rocks, when you go to phase 2, you have to remove your rock structure. Reason why? Because when you do subsequent land treatment, right, like PVD or stone column, right, it will hit the rocks. But with the geotubes, right, you do not have to remove the tube. So you can go from one phase to the other phase and to the next phase. Yeah. And this actually is much more economical compared to conventional these armor rocks removal systems. Yeah. Okay, this was the original design. Original design, you have the primary and the secondary armor rocks. This the core. Yeah. So from the Lac William Bridge, the owner saw the Lac William Bridge and they changed from the original design to a tube design. So we have the 2-layer jaw tubes over here. Yeah. And this is around 3.5 meter, and this is above the return period. We use a sandfield mattress. And it's behind the dike, right? Behind the dike, because this area high fall is subjected to typhoon. So I have another tube over here. This to prevent failure due to the overrun. So what I'm trying to say is that you can have the option of using a geotube dike to replace the conventional armor rock rebatment systems. Yeah, the soil is very, very soft. So we have to lay a high strength basal reinforcement 800 kilonewton to take care of the slip plane. And because of the submarine clay, I use this bamboo raft, yeah, to form the grid. The project that we've done in Indonesia is in Maya Grisid. We use this type of approach also. Maya Grisid container pot is the same we are used. So what I'm trying to say is that you're going to lay the bamboo raft. Then after that, you lay the basal reinforcement on top. Then you put the geotube on the left and the geotube on the right. So from there, you form your dike structure already. Yeah, you can see from here. This geotube dike structure. This is a phase 1 in 2017. Over here, phase 1. So, I mean, this geotube structure, right, it has to be there throughout each land reclamation phases. And each phase is around 5 to 7 years. So the geotube should not degrade. It should have the weathering and the UV resistant to withstand this high weathering and UV resistant. This phase 1 2017. Because they managed to sell the land very fast. So in 2019, they actually extend this out. So this in 2019, over here, these are geotube containment dike structure again. Yeah. So you can see from here, there's a phase 1 over here using geotubes. And from there, we go to our phase 2. And this is phase 3. Yeah, phase 3 over here. So I will just show a video clip afterwards. So you can see that each phase, like, the geotube should have very high UV and weathering resistance because there's no cover required, yeah, for each phase. This phase 1. Okay, I'll just show video clips. So these are the geotubes containment dike. Yeah, over here. This is phase 1 over here. Yeah. So after phase 1, they sell all the land over here. Then they go for phase 2. Yeah, this is a phase 2 over here. Yeah, the one in green is a sandfield mattress. This is above the return period. So once you have this this dike structure up with it, then you can do your land reclamation inside. So the geotube will actually protect whatever you feel inside here from being washed away. Yeah, these are the scour protection tubes over here, or scour protection mattress. These are the tubes. These are the sandfield mattress. Yeah, and these are designed to Kerr 217 design guide. Yeah, you can see from here, should have very high UV and weathering resistant the tube to form the containment dike. So this actually offer you a so-called a option compared to using conventional armor rock systems. Yeah, you can use a geotube with a scour mattress and the sandfield mattress to replace your conventional armor rock rebatment system, especially for land reclamation projects. And these are called sustainable growth. It saves the carbon footprint also. Yeah. You can see from here, this is the Lac William Bridge over here. Yeah, these are using the geotube to form the coffer dam. And this is 2017. Yeah, over here. This is the scour protection mattress. This is a sandfield mattress above the return period. This is 2019. It allows vegetation to grow. Yeah, from there. Okay, so from this Lac William Bridge, right? Actually, and from there we go to deep sea 2A, and from there they do an extension. This is deep sea 2A. So you can see that this is the Lac William Bridge which I showed earlier. Yeah, this is to build to the deep sea container port, and from there This is deep sea. This is phase 1. This is phase 2. And this is phase 3. Deep sea 2A. This is phase 3. And these are using geotube to form the dike. Yeah. This is the dike. And this they have used the temporary depositing dike, right, to trap the sediments. Yeah. This is a very innovative way. So they trap the sediments. And with this type of methods, right, they actually require to fill less because they trap the sediments. These are using geotube dikes over here. These are still leaving open, so when the wave comes in or the current comes in, it will trap the sediment, and from there, after that, they will close this the final dike closure. So it means they fill less because it's allowed entrapment of sediments. And this is how it looks like. Yeah, this is the so-called the dike over here. Then from there, we have secondary dike over here to trap. This shows the containment of the dike, 3 layers, 3.5 meter. This is the scour protection dike over here. Yeah, you can see from here, this is the deposition dike around trapping all the sediments. So once they do the closure over here, they fill less. Yeah. Okay, I just show this is a video clip again. This is deep sea 2A. This is deep. This Sosrobahu. This is another developer. So you have this dike, right, going all the way out into the sea. Then from there, you will move onto the right to form the containment dike. So with this type option, you do not have to use rocks. Yeah, because rocks, you have to bring in the rocks, which is so-called use more carbon footprint, and in terms of cost is higher. In terms of the so-called speed of construction is slower. Yeah. Okay. This is Sosrobahu. Then reclamation over here, they also use a tube to form the containment dike. Yeah. This is the secondary dike over here to trap the sediment that actually wash in. So you have 2 layers at the bottom and 1 layer on the top to form the 3.5 meter dike. And the requirement of the tube, right, it has to have very strong weathering and UV resistance. You need to have strong weathering and UV resistance required. This is Sosrobahu. This is another phase. This is the deep sea 2. Deep sea 2A over here. So you go all the way into the land. Yeah. This deep sea 2 over here. Okay, so from Vietnam, we go to this Philippines, Davao Coastal Highway. So for Davao Coastal Highway, because to solve the problem of land acquisition, yeah, normally if your land acquisition involve, so-called land that belong to the people, it will get very, very sticky or very, very messy. So what the Department of Highway or the Philippine government had decided to do is that they will offset the highway to the sea. Yeah, so this is where we call it the coastal highway. So in this case, right, they do not need to acquire land, because when they acquire land, it becomes sensitive. The politician will come in, the project will not be able to move. You see, so there's an offset about 100 meters from the houses over here, and from there we will build the Davao Coastal Highway. And this is, and when they do the Davao Coastal Highway, because it's subjected to the wave pounding and also to typhoon, we need to have a geotube to form the containment dike during the land reclamation before we actually put the deflective wall and the armor rocks in the front. So this is required. Yeah. Yeah. Because in this area, it does not consist of pure sand. So it's sand with stone. So in terms of approach, I cannot use this pump to pump, because the rocks will actually break the impeller of the pump. So we use the hopper systems in this case. So the hopper system allows sand together with gravels to be put into the hopper, and I use the water to flush the sand slurry and this stone into the tubes. Yeah, you can see from here, these are the tube containment dike. These are the so-called the property, yeah, that you do not want to acquire. So we have an offset. This is the highway, offset from the land, from your list of property over here. So we do the offset over here. You can see from here, these are the villages. Over here, we don't acquire the land, we do an offset. So you need a geotube dike to form the containment dike before you put the reflective wall and the armor protection system over here. Yeah. once then after that, I put the secondary armor rocks over here. It covers the tubes. You can see from here, if you were to acquire the so-called the land over here, the project will never, you can never start the project because there's too many property that you have to acquire. So because of this, the Department of Highway of Philippines, they actually do an offset. Yeah, the tube form this land over here. They do an offset, and you need a tube to form the containment dike because there's a lot of land, a lot of sand filling over here, and you need to trap the sand. Yeah, so I'll show a video clip on these projects. This is the Dawa Coastal Highway. Yeah, you can see that there's so many villages that they do not actually want to acquire. The filling stage, the containment stage, and for that the structural stage. So the tube forms the dike, yeah, of the reflective wall. This is the frame that we use for filling the geotubes. Yeah, we use a submersible suction pressure to pump the the water into the tubes. Dewatering and consolidation. But once you pump that, the water will flow up, it will tube the sand. I put a protection layer before I actually cover with the armor rocks. Dumping of the armor rocks over the tube. So we put a geotextile protection layer over the tube. Filling operation. So you can see from here, right? We actually sand with gravel. You actually put into the hopper, then use water to flush the sand slurry and the stone into the tubes. The hopper systems that we use. This is the basal reinforcement. Because the soil some area is very soft, so we have a basal reinforcement to install behind the geotextile tubes. The embankment failures are filling behind the tubes. Okay, so this is the highway stretch over here. Right? There's offset. So we don't acquire the land over here. 2020 update. So you need the tube to form the containment dike. So whatever you fill inside it does not actually wash away because this area is subjected to typhoon. A review of the sand deposition. So you can see that you need a tube to form the containment dike. This will form the stretch of your highway. This is the coastal protection area. Work in progress. So the geotube act as a dike to prevent the sand from washing away, and they allow actually for you to have a platform for you to do your structure. I use the coffer dam method because the sand over there consists of stone. So with the coffer dam method, it allows you to put the sand together with the gravel into the tube. The distance is 5 meters center to center, the distance for your filling. As I highlight, it's environment friendly because you know now actually the important rocks to form your it actually replace your core. Okay, so this is the geotube dike over here, and this is the reflective wall. So it forms the core for your land reclamation over here to form your Dawa Coastal Highway. This is the completed projects already over here, yeah, and this is up already. Okay, so from there, you can also use a geotube to form the breakwater. This is in Cancun, Mexico. So this is for the land protection immediate. This is a submerged breakwater, yeah, over here. So this is another type. This is basically it's a coarse fiber geotube. It allows marine life or sea barnacles to grow over it. Yeah. This is the, once we install the tube, this is during the low tide, and this is during the high tide. So I call this the low crest breakwater. And from there, I would like to take you to Penang. This is a very difficult project. The water depth is around 10 meters. These are phase 1. This is phase 2. These are using the geotube to form the dike, and from there I will do the closure. This is the land reclamation for this island, STP2 over here. You can see from here, these are the geotube to form the containment dike for your land reclamation. This is phase 1. This is phase 2. Yeah. So what we're going to do is that we're going to use the tube to replace the core of your breakwater. Yeah, the water depth is about 10.5 meters. So I'm going to use the geotube. I do not need a rock core. I'm going to use a tube as the core. Yeah. Here, because I'm working away from the land, so I need to have a working barge and also a transportation barge, and also a barge for the mixing of the sand slurry to pump into the tube. So altogether 3 barge, a crane barge, a working barge, and a transportation barge, a sand barge. Yeah. In these projects, we actually have a GPS system mounted onto the frame, so that when we lower it down, we know the exact location of the tubes. Yeah. This is the length of the tube is 50.5 meters, lifting of the tubes. Yeah. This is 50.5 meters, so I will lift the tubes. And this is the working barge. At one time, we will actually use 4 pumps to pump into the tube at one time. Yeah. So before I actually lay the tube into the water, I will connect the 4 pump onto the inner port, and from there I will lower it down. Once I lower it down, I will start the pumping. So at any time, it's 4 pump to pump the sand slurry into the tube. So with this method, I actually minimize divers, the use of divers, to install the sand slurry pump or the sand slurry pipes onto the tubes. Yeah, you can see from here, this is lowering of the tubes. These are the sand slurry pump on the barge. Once you lower it down, then from there you can see from here, this pump number 1, pump number 2, pump number 3, pump number 4. So anytime, right, we will actually connect 4 in the number 1, number 2, number 3, number 4. And once the tube are lowered down, then we will start pumping to pump 4 inner pipes onto the tube at one single time. Yeah. Okay. Last but not least, I will cover some of the innovative projects that we have done. So in this project, right, it is in Singapore, Pulau Tekong. In this case, we do not use sand. We use marine clay mixed with cement. Marine clay mixed with cement because our sand is very expensive. So like Singapore, they would try to minimize sand. So it's marine clay mixed with cement, and we want to lower the tube right onto the seabed. So the mixing was on the barge, and here we have to devise a lifting mechanism to lift the tubes onto the seabed. Each tube weight about 200 tons. Yeah. So here we actually designed the reinforcement is using geogrid 400. We designed this lifting mechanism based on friction to actually lift the tube onto the seabed. Yeah. So this is pumping the marine clay mixed with cement on the barge, and from there we lower it down onto the seabed. Okay. This is another project that we done in Indonesia. So in this project, we have to actually do a dewatering. This is a mining project. So we have to do the dewatering of this slush that's contained of coal, and from there we have to do stacking of 12 meters high. So you can see that 6 layers. Each layer is 2 meters. So we have to do 6 layers of stacking. So this actually involves geotechnical design, and I call it. As a geotechnical engineer, we can actually help to design for this stacking to ensure that the structure is safe during the dewatering, to ensure that the structure is geotechnically stable. Yeah, when you do the stacking layer by layer all the way up. Yeah, this is another project we done in Singapore, because in Singapore we be talking about sustainable growth. Lower the carbon footprint. So instead of using concrete structure on a normal so-called turf facing, we use a special type of bags. They have pocket to allow vegetation, special vegetation that you can put in the pocket. So this is how it looks like. Original slope. So we have bags with pockets over here. So you can actually insert your different type of vegetation you want into this pocket, and we have drip irrigation system running here. So once it's been done, you can actually have this type of so-called green structure to your housing scheme. Yeah, especially on the HDB, apartment or HDB flats. Yeah. This is done in Australia. Australia, especially in this area, we have to treat this a PFAS chemical. So we actually design a very porous bag that we actually fill with activated carbon. This fill with activated carbon. These bags are basically very porous, allows the water that contain PFAS that flows inside react with the activated carbons. Yeah, and from there, once the activated carbon treats the PFAS, then they can remove and add in additional one. But the design of the bags, right, high UV, very robust, and also very high water flow, so that the PFAS can just flow into the activated carbon. Last but not least, this is one of the projects we done in Singapore. This is in the floating solar panel, but because of debris that actually damaged the solar panel, we actually had to design a so-called a debris containment system to encompass the whole area of this so-called solar panel. So it prevents the debris from flowing inside to damage your so-called your panel. So we actually designed this high UV, high weather resistant to protect debris from floating inside. Yeah, the last project that we done is in the Maldives. So in Maldives, because normally you use a tube, but because over there tube was not option because the project was small. So we actually designed a cellular bag system for the land reclamation. So with this, I thank everyone for your time, and I wanted to open this to the floor if there's any question from the floor.
Okay, thank you so much, Mr. Lim.
Welcome.
Please raise your hand, or you can write your question in the chat box. So maybe I will check my chat box. So there's a question here, Mr. Lim. So you've many countries you've already applying these techniques. What are the challenges that you can maybe share with us regarding the installation of the these geotextile tubes?
Okay, I will discuss about the challenges in Indonesia context. I think that would be fair. So in Indonesia, we are done in Ancol and also in Maya Green Seed container port. So one of the challenges that we found is that the pump. I mean, because you have to use a high flow pump, at least about 190 meter cube an hour. But from the local context, in terms of the contractor, right, some of them do not have this type of high capacity pump. So when they try to pump, right, they can't actually inflate the tube. So this is one of the so-called challenges. But I feel that it can be overcome because as long as the project is sizable enough, the contractor will be so-called willing to invest on the pump. Okay, thank you.
Thank you. So so almost there are no limitation to implement this technique, or there are some specific characteristics or site-wise condition that can be maybe perfect or good for applying this technique.
Okay, I mean the other so-called I will put it in a way that, okay, when you use the tube or when you don't use the tube, yeah. So if the water level is very deep, I can say that if anything, let's say more than 5 meters, in that case you will need divers. You need a so-called skilled contractor. But anything if less than 5 meters, it should not be an issue for tube installation. When it's go above 5 meters, in that case you need a highly skilled contractor, and the contractor also need to have the equipment to do the tube installation and also to do the tube pumping. Other than that, should not be an issue at all.
Okay, thank you. There's a question from Miss Etri. So she asks, can this innovation lower tsunami waves, for example, beside the breakwater construction?
Okay, so we have to ask ourselves the question, so where do we use the tube? So for tsunami wave, right, in that case, we use the tube as a breakwater, or as a breakwater to break the energy, yeah, of the wave. And this is very so-called widely used, especially in US, in United States, because they use a lot of this as a submerged breakwater to break the energy of the of this wave energy. And we have also used mainly in Vietnam also. In Vietnam, especially in the area, in the high form area near the north, we're subjected to typhoon, is it? Typhoon. When typhoon, there's a surge in the wave, is it? So this one, it will break the energy before the wave actually reach the shoreline. So the answer is yes. And this offer a so-called a green solution because you do not have to import in the rocks, yeah, and a lower carbon footprint, yeah. Okay.
So maybe this relate to the next question by Pak Tony Kurniawan. The cost between the tetrapod or rock boulder that you just mentioned to build the breakwater compared to the geotube.
Okay. As long as that at the project site, right? Maybe I put in a way at the project site, if you don't have rocks, right, the tube will be a better option because you don't have to import, yeah. But then the coming to that moving forward, whether you like it or not, at the end of the day, you are not allowed to blast rocks moving forward because of this carbon footprint. Everyone, I mean, because of this so-called this change in the weather, you got flooding everywhere, right? So we actually have to move away to use less rocks to save the carbon footprint. Yeah. So to answer the question on the cost, right? If there's no rocks at the project site, the tube will be a better option. It saves your carbon footprint. Yeah.
Okay, thank you, Mr. Lim.
Welcome.
And another question from Muhammad Aswin. What is the resistance of geotextile tube due to the aggressive environmental such as seawater or regarding the material of the tube?
Okay, the material of the tube, right, is made from polypropylene, PP, yeah. So PP, if you talk about the chemical resistance, right, from pH 2 to pH 14. So there's no so-called breakdown of the bond, right, to high chemical resistance, I mean high acid and high alkaline, and also hydrolysis. But the key thing is on the weathering impact, because okay, on the chemical pH 2, pH 14, seawater is not in the acid and alkaline, right? So it's on the weathering. So this is where we actually put it down, right? We actually have to test it, when you do a design, right, you have to put down in the spec, right? The tube must subjected to so-called a very stringent testing under the ISO standard, so that when they test it, you should have a design life for 120 years. And this is the weathering test plus a UV so-called testing. So you have to so-called put it down in the test. Therefore, the project that we done in Vietnam, right? The client only need 7 years, no rock cover. So we can actually design a fabric for that particular duration. Yeah, on that. Compared to the normal type of fabric, let's say if you available in the market, right? Some in 1 month, right? The loss of strength can be easily 70%. Yeah. So you have to ensure that the standard is correct. Yeah. For when you actually put into the tender document, it has to have high UV and high weathering resistance on that.
Yeah, thank you. And how about the friction capacity regarding the horizontal load, such as wave or seawater? So this one is the load.
Maybe
yes.
I was just share how we actually, the last one, how we actually do the design. I think that would be easier. Can I, let me see. Wait, let me do a share, let me just share. Let me just share one. Screen. Can you see my screen?
Yes.
Okay. So normally when we design, right, this is the design parameters. So it means that the significant wave height divided by the relative volume mass of the material used times the width of the tube, right, should be less than 1. So this is designed for the wave attack, you see. And we also have to design for the current attack. The current attack means that it's critical velocity, right, divided by the square root. G is the gravity acceleration times the thickness. I mean, sorry, this is the relative volume mass times the thickness of the tube should be less than 1.2. See? So these are what we design. I mean, in terms of the so-called on the current attack. And since we are here, right, I would like to cover, and these are the other check that we check. So we had to check that there's a cell weight of the tube, right? is enough to receive the lateral air pressure when you do the backfill. But before that, we actually have the pull out box test and these are friction resistance test of the tube with the soil. So I actually have the friction angle between the tube and the soil, and from there we will actually calculate the sound wave versus the active pressure acting behind the tube. So since we are here, I want to share just now we are talking about, okay, this is the test. Okay, so in here what we are trying to say is that this you have to actually to specify to ISO 13438. And in this test that we are going to say that in the lab, right, if it's 112 days, you test this in the lab. And if you have a strength retention of more than 52%, the design life is 100 years. So these are the tests that actually you have to specify ISO 13438 and also EN 1224. This is basically on the UV resistance of the tube fabric against the UV resistance. Okay. So I hope I answer your question on that. Thank you.
Okay, thank you so much, Mr. Lim. Maybe we have come to end of this session. Maybe I will have a short remark. So in applying this tube, you need also to conduct a thorough site assessment and follow the best practices for the installation. You have some more remarks, Mr. Lim, to end this session?
I fully agree. I think because we actually designed to curve to one cell. So for a good design, you need the input parameter, you need to especially on the wave and also on the underlying soil, so that you can actually design correctly on the geotechnical design. But what I will offer is that if Bino University, if we need, let's say a half a day workshop on this, then we can actually go through on the design. I actually offer myself on that if you need to.
Thank you so much for your offer, Mr. Lim. So we come to the end of the session. Thank you so much, Mr. Lim. So I will hand this session back to MC Anggi.
Yeah. Thank you, Dr. Yureana, for taking over. And thank you to all the speakers for such inspiring insights. I hope everyone find today's presentation useful and informative. I'd like to apologize for the question left unanswered due to the time constraint. Before ending today's session, I'd also like to remind all participants to fill in the exit ticket. We would also like to inform to all the attendees that the certificate will be delivered to each of you by email with no later than 7 days within this webinar. Before fill in the exit ticket, I want to ask everyone to wrap up our today's session. I'd like to invite everyone to turn on your cameras for a short documentation session. For the documentation, Gabriela.
Okay, everyone. I will screenshot from slide 1 until slide 6. Get ready. 1, 2, 3. Okay, wait. Okay, slide 2. Slide 3. Slide 4. slide 5. And the last one. All right. Is the exit ticket. So the participant can scan this barcode or type the link to record your attendance. Thank you.
Okay, bye. Thank you, Mr. Gary. Thank you, Mr. Lim.
Yeah, thank you very much. Yep. Have a great day.
Thank you, all the participants. You may leave.
Unfortunately, we have now reached the end of the seminar. And once again, the entire Civil and Environmental Engineering Technology Seminar Committee would like to extend our gratitude to our honored speakers and Dr. Yureana for participating in the integral part of this event. We'll also like to take this opportunity to thank every attendee for your active participation in this seminar. We hope everyone enjoyed the program we work hard on. And with that, I bid everyone present goodbye. See you on the next seminar. Thank you for your attention. Stay safe and have an amazing rest of the day. Thank you.